5 more minutes. Let's see, because today is the last. I better start the class now. So nice, 9:11 a.m. So we will start the class. Okay. So yesterday we'll go through the ACL, access control list, and then AAA, and then IPsec VPN, and also the GRA VPN. And the last topic we go through yesterday will be the SNMP. Okay, so we finish all the modules. So today we are going to a new module, which is the IPv6. We have 3 IPv6 topics. First one will be the introducing the IPv6 networks. In this topic I will talk about the basics, some IPv6 basics, just like the IPv4. And then we will go through the routing technologies in IPv6. So we'll only look at the OSPF v3. Okay, and then we will look at the application layer protocol, or the service application layer, which is DHCP v6. And then after the IPv6 topic, we'll have the another new module, which is the MPLS basic principle, and also the segment routing, or we call it SR basic principle. So let's go into the IPv6 networks. So with the gradual exhaustion of the IPv4 address space, new solutions for continued address spaces were needed. Okay, so as I mentioned in the network address translation class topics, so I mentioned that the IPv4 address is keep on depleting. So it's depleting very fast. Until today, all of the IPv4 addresses are already assigned to either to an ISP or either to any cloud services or the data centers have acquired all these IPv6, this IPv4 address range. So if there are some more new ISP or the current ISP or other service providers, their request for more IP addresses. So now we don't have enough IPv4. So we hope that we want a long-term solution. We want a IP address range that is there's a lot enough to, you can say, almost unlimited. Okay, so we need some solution for continued address space. So before we have the long-term solution, we are using a temporary solutions. We call that NAT, NAT. Okay, so in order to so this IPv6 addressing architecture is the long-term solutions for IP addresses. So because IPv4 and IPv6 is really a big difference, so in terms of number of bits, it's already very big difference. IPv4 you have 32 bits, and then but IPv6 you have 128 bits. So because of this, the transition to an all IPv6 architecture, you require major changes in your protocols, or maybe in your applications or your standards. So we still have some of the current TCP/IP suites will still support the IPv6. Later we'll see the layer such as the TCP layer will be the same. Ethernet layer also will be the same. So then we'll see how is IPv6 looks like. Okay, so let's see. So I will explain the characteristic of IPv6 and then the IPv6 format and addressing types. And then I will also go through the process for IPv6 stateless address auto configurations. Okay, next. So IPv6 addressing. So this is IPv4 32 bits. So how many IP address can be shown using 32 bits? It will be 4.29 billion. 4.29 billion. But some of this some range of this 4.29 billion some range IP address is being used as the private IP, and then others other uses for public IP, and also special IP range or the multicast, and also for the experiment like this. Okay, so for IPv6, we have more bits. 128 bits is 4 times from the IPv4. So this is how to read this. Is 340 under ceiling. 340 under ceiling. Okay, so the exhaustion of limited IPv6 address space, IPv6 address implemented to resolve address shortage. So by using this IPv6 address, we will have enough a lot of IPv6 address. So we even can cater everyone. I mean, or actually every device that can connect to the network, they will have they will have a public IP. But this is the public IP will be the IPv6 form. But in IPv6, we don't no more calling that public IP, private IP. No, because in IPv6, we got no public and private, so that we don't have net addressing, network addressing. No, network address translations. We don't have this network address translation. Okay, so this is IPv4 IPv6 header formats. Okay, you can see this is still data. Say the same thing, data, and this is a TCP header. Say the same TCP header is about your source and destination port numbers. But this one IPv4 is replaced by a IPv6 header. So the IPv6 header, you can see, has been streamlined to reduce overhead. So you can see. So for the first field, we still have the versions. In the version, it will show 0110 means 6. And then the traffic class is used for quality of service. And then flow label. So what do you mean flow label is? So all the packets, IPv6 packets, they have the same flow label. Okay, source and destination IP address will be sent through the similar, same path, similar path. Okay. So and then you still have your payload length, the size of the data. Okay. And then next header. What is my next header? In this situation, my next header is a port number, showing port number 6. So this is TCP, means 6. So what's the hot limit? Still the same, 255. Of course, the most important is the source and destination IP address, 128 bits and 128 bits. Okay, so In IPv6, there's something special. We call it IPv6 extension header. So extension headers are used to support parameters that are not required in every packets, in every IP packets, such as fragmentation and IPsec. So if in your IPv6 network you don't have a fragment, or you don't connect to IPsec, maybe you doesn't need this, doesn't have to use this extension header. So this is what we call the IPv6 basic header. Extension header is example fragment. So when you need to do the fragment, then only the fragment header will be added, will be encapsulated into the IPv6 packet. So in here we can see that the next one is still TCP. Means that this next header is TCP. So it's reserved. This one is reserved and fragment offset, reserve, M, and identification. M is the flag. So you have M offset, your flag, and the identifications. Okay. And then, such as this, the last sentence here, such as fragmentation and IPsec. So IPv6 also already have a encryption or a VPN. So the IPsec for this IPv6 essentially is just a header, extension header of the IPv6, the VPN, the IPsec VPN. So you can see the IPsec, IPv6 is far more secure than the IPv4. Okay. So this is the IPv6 address architecture. Okay, IPv6 total 128 bits. So that if I will ask you to write 28 bits, 0, 1, 0, 1, 0, 1. So how much time you can do this using only? IPv6 consists of a prefix and interface identifier. Addresses are commonly displayed in the hexadecimal format. So if you want to write the 128 bits with very long numbers, sometimes you might type the wrong, it's either 0 or 1, you might type the wrong numbers, or you maybe, okay, mostly it's typed with the wrong number, and then maybe a network, okay, doesn't compatible with IPv6 also possible. So regardless of that, we can write the IPv6 in hexadecimal formats. So from the example here, you can see this is 2. This is the binary form of 2. This is a 0, 0, then 1. So it means that one hexadecimal number is 4 bits. 4 bits. 1, 1, 2, 3, 4, 6, 5, 6, 7, 8. Okay, 10, 11. Okay, 12. Okay. Then this. Okay. 4 bit, 4 bit, 4 bit, 4 bit. It forms a 2001. Okay. So for IPv6, the front part actually mostly is a 64 bit. We call this IPv6 prefix. You can just say that it's just like your subnet mask, or I should say network address in your network. So your network address, let's say you have network bits, network address means the other behind are all host bit, but here we call this interface ID. IPv6 prefix and interface ID. So addresses are commonly displayed in hexadecimal format in IPv6 architecture. So there's some IPv6 address condensing. So this is very important topic because every time the exam will ask some kind of these questions. So what is address condensing? It's a condense from your route for your full IPv6 addresses. Okay, then further condensing into one IP address, a shorter one, and then configure everything. Configure until it becomes a most simplified form. So addresses can be condensed by removing the leading zeros. So the double colon operator will further condense strings of 0 values. Okay, so this is condensed. So IPv6 address reservations here. So in IPv4 we have classes, class A, B, C, D, E. But in IPv6, because we have too many IP addresses, too many range. So it's time. So here in IPv6, we don't categorize using the A, B, C, D. It's just called the IP range and what is the description of this IP. Okay, so the first one, we call this current global unicast range. Global unicast range. Okay. Sorry. Oops. Okay. So IPv6 address reservation. I just notepad. I want to write something. Okay, so you can say that global unicast, global unicast is actually equivalent to public IP. To public IP in IPv4. So global unicast. So in IPv6, all network devices can have this global unicast address that may have. Okay, so that's why in IPv6 we have too many IP addresses. We can even provide every device one IP address also can. So how to differentiate? What is the global unicast range? What's the range from what to what? Okay, so from here I can see 2000. Okay, 20000. Okay, and then /3. So let's turn this /3. /3 means that the first three bits remain the same. It's fixed. So 2000 double colon 3. So what happens? Oops, shouldn't like 6. So what is global unicast? What do you mean by this first 3 bits? It means the first 3 bits. Actually, inside this 2. Convert 2 to binary. This is 0010. Then 0000. Okay, and then 0 dB8. 0 dB8. Oh no. Oh sorry. No. Sorry. So what I want is just to convert the 2 to binary, which is 0010. Okay. Okay, we see that. This is the first 3 bits, 001. As long as the IPv6 address, the first 3 bits is 001. So this will be a global unicast range. So let me ask you some questions. What is 2000? No, 3000 double colon /3. Okay, what is this? Is this a global unicast IP address? Global unicast IPv6 address. Is this? Okay. Oops. Okay. Okay. Where is it? Okay, so is this 3000 double colon /3 is the global unicast? Yes, we can check. Let's see if we change the 3 is to 0011. Okay, then we look at the first 3 bit, the first 3 bit here, the first 3 bit 001, okay? 001. So you will see it same as the 2000, which is 0010. Okay, so this will be the global unicast. So next one, how about 4000 double colon /3? So what do you have? 4. Change the 4 to binary, it will be 0 1 0 0 1 yes 0 1 0 0. Okay. So is this is not a global. So this is 010, not 001. So from here, when you ever see a IPv6 address, start with 2 or start with 3. So you can almost make sure that it is either global unicast, is a global unicast. So either you come from the ISP, okay, or sometimes not. So regardless, you see 2 and 3, you confirm that's a global unicast IP. So second one is the 200110 dba /32. So this reserved for documentation. You can see this one is actually part of this global unicast range. Okay, reserved for documentations. So next, this is the link local unicast address range. Link local is actually same as your let me see. No, it doesn't mean anything. So link local unicast address range is IP address that is self-configured by the by the end devices, so by your PC. Okay, self-created link local unicast address range. Include the router and switches also can do this. Okay, link local. So and then you can have a multicast address range. We start from FF/8/, means the first FF should be forever FF. So it means 1111 1111 FF. So for link local again, it starts from FE80, and then it's the unspecified addresses, which double colon /128. This means it's not it means don't have IP address. But in your for loopback, even though you try to ping the loopback addresses, you will still reply even though even though you can have this double colon /128. Okay. So or you also might have a loopback IPv6 address. It's a loopback address. Okay. So means it's double colon 1/128. Okay, address range have been allocated in IPv6 for unicast and multicast, along with special addresses for operational support. So if you do notice, in this IPv6, we don't have any support. IPv6, we don't support for broadcast. Okay, we don't support broadcast. Instead of that, we use a multicast. They say we see how the IPv6 utilize a multicast to forward the data. Okay, next question. Okay, so IPv6 addressing Unicast. Unicast I already explained to you. Okay, the last 64-bit means you always go by half. The last 64-bit is a interface ID. Okay, the first 64-bit is the global routing prefix and the subnet. Okay, so and then below here is the FAT, the link local. So again, the link local address is the equivalent to what in the IPv4 is the RP bar. Okay, the 169.254. So this MAC address is self-generated by this IPv6. So prefix, so global unicast address prefix are used for public network. So prefix range are reserved for various IP transmission methods. So this unicast. So remember, in IPv6 we don't have broadcast. Okay, so next one we look at the multicast. So is FFFF, and then pay against the okay. So this is FF. So yeah, first another next 4 bits is flagship flex, the flex. So next for the next 4 bit will be the scope, and the next 112 bits is a group ID. So you can say at the front okay, at the front this is the multicast ID. So you look at the below here, the table is here. So if you put this IP address, multicast address FS02:1, and you send, it means this is designated for the destination to the all nodes address. So the all nodes address means all nodes means all your network devices, your router, your switch, everything, all nodes. So that's why you can see instead of using a broadcast, we use the multicast in the IPv6. Okay, we use a multicast as the broadcast, the kind of the broadcast. So and then reply with FS02.2. So also means all routers. Okay, it means all routers. So means the PC you can use this, or the host can use this. Look for its gateway. Okay. Okay. So multicast addresses are distinguished by an FS00:8 prefix. So select multicast address group are reserved for protocol use. Okay, so okay, so in IPv6 we have a new type of forwarding. In here we have this Anycast. So Anycast allows multiple instances of service to be associated with a single address. You can see, enabling a variety of service applications. Okay, so Anycast, you can say that this is the concept is, let's say unicast is 1-to-1, multicast is 1 to a group, broadcast is 1 to all. For Anycast is 1 to the nearest. What do you mean by 1 to the nearest? Let's see. Anycast allow multiple instances of service to be associated with a single address, single IPv6 address. can be used for multiple service. Okay, so what do we have? Here in the example on the diagram, we have zone X, we have zone Y, where we have a host for zone X and host for zone Y. So and then we have two HTTP service. We can assume that this is a web service where two sites, two different locations providing the web. Okay, HTTP service. But do you notice this? The IPv6 address for both sides is the same, 2001:0DB8:842. So they're using the same IPv6 address. That means, let's say, if any user from zone X try to access some IPv6, try to access this IPv6 address. So it will be directed to the nearest HTTP service. And then for zone Y, so for zone Y, if zone Y try to access the same IPv6 address, it will be directed to this one. Okay. This is to avoid congestion, for less congestion we have, and also we can do for load balance. Means that maybe zone X suddenly the traffic flow at zone X it become very high, so maybe you can redirect some traffic, okay, to another server. Also, this also can be just a backup. Let's say there are two HTTP service, two different sites. So if let's say if this link is down, all the traffic for zone X that wish to access the same website will be redirected to this route. Okay, so this is Anycast. So IPv6 stateless address auto configurations. So hosts, IPv6 hosts are capable of generating IPv6 address independently. Means all the hosts can generate his own IPv6 address. Okay, so router advertisement deliver network parameter information. What the PC here do is, so the router write the solicitations. Okay, so after running this, solicitation means look for the router in this network. Look for the router, or which also means that it means look for the gateway. So the ICMP type for this will be 133. Okay, and then the destination FS02:2 means all routers. So this is using ICMP type 123. This is using ICMP type 134. Okay, so it's source. So you can say this router received this RS. This router reply with the RA. So source equal to okay, the router link local address. Source on router link local address means that is the router FEAT IPv6 address. So and the destination FS02:1. Okay, :1 means all not sent to everyone. So the data, your lifetime, current home count, limit, autocomplete flag, and options, the prefix. So the data host send this router solicitation. So any router or any device that can support this will reply to PC, okay, which is using advertisement. Okay, so US64 for IP stateless. IP stateless. Let me see. So US64 for IP stateless or address auto configurations. That's why. So how the PC can self-generate a DHCP. No, I should say the self-generate a stateless address auto configuration. Or I should say, okay, that is the stateless self-generate IPv6 address. So how to get this? This is the from routing solicitation, PC send, then the PC receive a routing advertisement. Inside router advertisement, the PC and the host can check. So the PC can check, oh, what is my gateway? Who is my gateway? Means that the first the first gateway. Okay. So the first 64 bit of my prefix, of my prefix should be same as my my gateway. The first bits, the first 64 bits. So after I get the first 64 bit from my gateway, okay. So I still have left behind 64 bits. How a PC can get it is by using the MAC address. I believe. So now all the network devices must have must have a MAC address and also an IP address. So, so in order to create the US64 for all different devices, so we can use this method. So, first step, you have to know where is your MAC address. Who is your MAC address? So after that, in between these 14 bits of FF, these two, okay. So what can we do here? Okay, from here you can see that the host MAC address is injected with a 16-bit FFFE values. So as well as a 7-bit is negated. 7-bit is already negated. So FFFE. Okay, after that, putting the FFFE, you already get the 64-bit. But if you further enhance, it becomes the UI 64 as a complete IPv6 address. You can use this. 7-bit is negated. So this is to generate the 64-bit interface identifier for the IPv6 address. Okay, so 7-bit is negated. Let us show you how is it. Because in exam, this question, you convert from 48 bits to US64 or from US64 convert back to 48 bits. So this is very important in the exam. So IPv6 stateless address auto configurations. So after the PC receives the IP address, so you want to apply. So before applying, you send a ICMP type 135, means is this address in use? Is this address in use? Okay, that's like a gratuitous ARP. But in IPv6, we don't no more have a gratuitous ARP or ARPv6 such as thing. No. So in ARP, we do the duplicate address detections through the okay. So DAD is still used for IPv6 to verify that an address is unique before it is applied to the host interface. So This 135. So router advertisement 136. Okay, very easy to understand. And then source destinations. FS. Okay. Destination. Let's see. FS02 double colon 1 double colon 1 colon. Okay. FF00 colon 1. So what if this? FS02 colon 1 colon FF. So this actually the prefix for a group called the solely-sided node. Solely-sided nodes. So all means all the IPv6 devices which have their which have their IPv6 address is checked and they are confirmed, they will have this FS02. Okay, double colon 1 double colon FF. So it might be appears. Okay. So some summary: what is the smallest condensed IPv6 value possible for address? 2001 0TBAs 00000000000000 colon 0328. So is for condensed, smaller condensed. This is 1. Okay. No, sorry. So how to condense? You have to always start the first the number of each group.
Sorry, Mr. Bay.
Yes.
Please, can you go back to the diagram again?
This one?
Yeah. The destination. I was a bit curious. Sorry, I missed something there. I was a bit curious as to
about this.
Are we looking at, are looking at the first 001 is missing in the second one, right? In the second host.
Where is this and why is this?
Right. Yeah, so the source there is zeros, here is having something, and then the destination here is missing the FFF001 for the host, the first host. So what is making it know that they are the same?
This thing. Okay. Data, who are using this, they are asking. So this is solely-sided node. This is a multicast
yes.
address. So the first 104 bits is fixed multicast for this solely-sided nodes. First 104 bits. So it means that the last how many bits do you have left? 24 bits. Isn't it? The first okay, let me check. So it's actually inside the slides. So the first 104 bits, 104 is the prefix for solely-sided nodes group. It's a multicast. So means that the extra 24 bits. Okay, and another 24 bits. So 24 bits. Where is the 24 bits at here? So we have 1, 2, 3, 4 here. Okay, this 1 and this 0. Okay. Okay. So this column 1 should be means colon 1. So here colon no 0, 0, 0, 0, 1. I should put it more clear. Okay, thanks. This 0, 0, colon 0, 0, 0, 1. How many bits is this? So this is how many bits? How many bits?
In hex or just in bits?
This is hexadecimal. When I talk about bits, this is for binary.
Yeah.
Okay. So how many bits you have in this? How many bits you have?
That's 16 plus 8.
24 bits. Okay, 16 plus 8, 24 bits. So the first 104 bits is the, sorry, fix, is the prefix for solid-sided node group. Okay, and then so you add with another 24 bits. So total you have 128 bits. Okay. So solid-sided node group means that, okay, let's say example here. Let's say this PC he want to use this IP address, the IPv6 address 2000:1. Then now he asking DAD. He tried to do a DAD, duplicate address detection, but actually this is just a name for this process. So the protocol, the packets are being used is still ICMP v6, ICMP type 135. So what is this solid-sided node group is when this if this PC is looking for this, he try to validate, try to identify is there any duplicate IP conflict. Let's say no one reply. No one reply. Here, what happened? The PC will use officially use this IPv6 address 2000:1. Correct?
Yeah.
Okay. For this, and when after this is confirmed, I can use this. Then this PC will be the PC will assign himself, put himself inside the solid-sided node group.
Okay.
I can understand this. Means that all the PC that put themselves in the solid-sided node group means that they already do a validation. Do this DAD, duplicate address detection. They already confirmed. Okay, there's no one inside the network use the same IPv6 address with me. So when there's another PC that join into the network, also want to use IPv6, that PC also will send a ICMP type I135 to do this, to do the DAD, to detect. So again, the destination also is the solid-sided node group. Okay, can understand this? And this, please try to memorize this. This 104 bits. Okay, FS02:1:FF. Okay, this one, because this will appear in the exam.
Okay.
Okay, means the last 24 bits. The last 24 bits is actually take from the here the last 24 bit of the address you want to use. So you might think that, okay, so because the last 24 bit is just the last 24 bit, maybe there are other addresses. Because there are many IPv6 addresses, it can be many IPv6 addresses with the same, with their last 24 bit is the same. Possible or not? Yes, it's possible. It's possible. Yes, it's possible. So actually we are looking for, even though we send this, actually they are looking for inside the data here is this. Here will be this. Okay. Just that all the router in the solid-sided node group, when they receive this, oh, I see FF, okay, 02:1:FF. Okay, I know that this is the solid-sided node group multicast. Okay, so since the router, I already verified my IP address long time ago, I already in the group, so I see this, I accept this. So if this is the, after that I read this, oh, this is data, the IP address 2000:1. Example for this, this guy is already, this PC is already in the solid-sided group. He checked this. Okay, I'm already using this. So It sends the ICMP type 126 source from its own IP address. Destination, this is what? All nodes. This does a broadcast, all nodes. Send to everyone. So data, then reply me. This means that I am using this address.
Okay.
So apart from this, okay. So for this condensing, can you let's go through this one again. So IPv6 condensing is, let's see. Before this, you can understand this a lot. Okay. IPv6 is 128 bits. 128 bits. You can separate into 4 groups. 1, 2, 3, 4, 5, 6, 7, 8. Each of the group have 16 bits. All these 16 bits is shown in hexadecimal. Okay, hexadecimal form. This is hexadecimal form. Again, this is each of these hexadecimal number means is 4 bits. It's 4 bits. Okay, until here. Okay, next. So how to do the condense? Again, this one. 8 groups. You can write all the hexadecimal number. So it's still very long, even though we already convert from the binary into hexadecimal. This is still very long. So we can further condense is by, the first step is by removing the heading 0. All the heading 0. Remove. So this is 0, 0, 0, 0. There are 3 heading 0. Okay, this 3 heading 0. So you only left 0, 0, 0, 0 for this. 1, 2, 3, 4. And this is, you remove the heading 0, 3, 4, 6. So this start with 8, no heading 0. This start with 0. Remove, you left DB8. So, okay, now this is a valid IPv6 address. Valid, you can use this. You also can use this. It's valid. You also can further condense using the double colon. Okay, you can further condense a string of zeros into double colon. And this double colon can only appear once in one IPv6 address. You cannot have 2 words like this. Cannot. So let's see. For this one, condense, because you must make sure you're familiar with this. Because condense is a very question that's always come out in the exam. Ask you how to condense, ask you how to expand, and what is the possible condensed form? Possible condensed form. It might be just remove the heading 0. Then you can see colon 0, colon 0, colon 0, colon 0. Because there are some students that might thought that this is just a process of the condensing. It's not complete yet. So the form, this kind of format cannot be used. But no, it can be used. So 0, 0, 1, let's see, colon 0 db8. Let's see, colon 0, 0, 0, 0, 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 colon 0, 2, 3, 3, 2, 8, colon 2, D, 7, 0. Okay, this one. So let's just copy this. Alright, let's just do this straight away. Okay, can I condense this? Condense by first step, remove the heading 0. Heading 0, remove. 4, 0, you remove the first 3. The other heading zeros. So this form works fine. You can assign IPv6 address using this form. Works fine. So you can further condense all the zeros into 2 columns. Okay. So on these 2 columns only can appear once in one IPv6 address, so that you can expand it to the original form. Can you do this? from here. So you always start with first one. Okay, the first one is 2001. Okay, I confirm that first group is 2001. Then colon. Okay, second one, DB8. Only 3. Means that, oh, I know that there are one heading 0 is being already removed. 0, DB8. Colon. Okay, how much it is? How many groups? How many groups of 0 is inside this double column? If you don't not sure, it's okay. You just continue the next one. This one, 328. I know that. One heading 0 is already removed. 0, 0, 3, 2, 8. Then colon. Okay. Then the next is 2D70. It's complete. 2D70 is not removed. Anything not removed at all. So endless. No more. So know that, okay, I have the first 2 group. And then the last 2 group means that in the middle here, I have I have 4 more groups. Since this is a double colon, I know that there are 4 groups of 0. So 0. Okay. Oops. Here. This one. So 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Now I can expand it back to the original form. But if let's say if you put here 2 double colon, it's very hard for you to identify how many in this, how many group of 0 in this double colon or this double colon. Cannot, you cannot identify. So you just put one double colon, you can identify. Please, you must be very familiar with this condensing and expand. Condense and expand. You must very familiar with this. Okay, and then how is it possible for an end station to independently generate an IPv6 address using this UI64? How? First one.
Inject the.
Okay, how you get that? You get the prefix. Prefix also prefix 64-bit from gateway. Gateway, because inside this network, IPv6 network, I'm sure I must have the prefix same as my gateway. Okay, makes sense, huh? And then the last 64-bit get from UI64 self-generate. Okay, so this is called stateless address auto configuration. Okay, how to get from the gateway? This one, router solicitation, and these are the prefix. Prefix. Okay, I get this, and then self-generate UI64, done. Combine, become a IPv6 address. So about this UI64, I have to repeat again. So how to get from your 48 bits of MAC address? So let's say I'm PC1. Here's PC1. I copy the MAC address of PC1. Okay. And then I paste it here. Okay. So this is 48 bits. So I need 64 bits. So how many bits I still short of? I short of how many bits? I short of 16 bits. Okay. So I can just put this in this form. See. Okay. How about I just change the dash to a colon? Okay. Understand this? But this is still for the bits MAC address. Okay. So in order to convert this to UI64 bits, this first step is step 1. Insert FE in between P3. like this. Insert FFFE in between. So go to the between, middle, here, FFFE, and separate with a column. Okay, so this is already 16-bit combined with the 40 bits, 64-bit. Okay, now we have get the 64-bit, and you will see the step 2. Okay, step 2, negate the which one? The 7th bit. 7th bit. If the 7th bit is 0, change to 1. If the 7th bit is 1, change to 0. So where is the 7th bit? Here, which one? Where is the 7th bit?
The F.
Again, where is the 7th bit? I say bit.
Oh.
Bit is binary form, it's bit. There is no hexadecimal we call bit. Okay.
Is it the 7th bit of the inserted value?
No. In this whole 64-bit. No.
Starting from the
64.
LSB?
Yeah.
From the LSB?
This one?
From the LSB or an MSB? Which position are we starting from?
Starting from the left, 64-bit. From the left.
That should be.
Where is the? It's inside the 4. Okay. 5 means 0, 1, 0, 1. So
1.
only 4 bit. And then 4 is 0, 1, 0, 0. So 1, 2, 3, 4, 5, 6, 7. This one.
Okay.
This is 0, so change it to 1.
Okay.
Okay. So this is still 5. 5, no change. We just change this. 4 change to. This is 6. Copy, paste. So this is the EUI64. Okay, EUI64. So let's say if you go to PC1, command, ipconfig. Okay. See the EUI64. Copy. You see, it's the same thing. Right. EUI64.
Okay.
So, and then what I want you to do is, okay, let's say the question gives you this. This is the EUI64. Please find me the MAC address. Get me the MAC address. How you do it? How can you do it?
So we are reversing backwards.
Yes, do it reverse.
The 7-bit has to be negated back.
Okay, negated. 7-bit, where is it? It's in?
6.
6. So what is 6? 6 is 0, 1, 1, 0. So 7th bit should be this one.
0.
So now this is 1, change to 0. So this is a 4. Okay, this is a 4. So I need the front, 5. Okay. And then, second step.
Remove the inserted 16 bit.
Remove the FFFE. Remove the FFFE. Correct? Remove. Then get back. 5489. Okay. This one, 5489, 984E, 2388. 5489, 984E, 2388. Okay, so you also must be familiar with this. From MAC address to EUI64, and from EUI64 back to MAC address. Okay, this is the very common question inside the exam. So that's all for there's some basic of the IPv6 address. Okay, from here, let's take a 15 minutes break. Let's take it. We continue X. Let's see, what's the time? We continue at 10:30. Okay, 10:30. So you take this time, try to digest for this the first topic of the day. 30 PM. Okay, so let's continue. So we have finished the IPv6 basic. So now we're going to next next topic. I'll look into the DHCP-v6 first, because we are using the same topology. This topology is for DHCP-v6. I can also using the same topology to show you how the PC do the stateless auto configurations. Okay. So let's see. DHCP-v6 in IPv6 applications. So again, DHCP-v6 also is the application layer 7 application layer, also running on UDP port. Okay, so the IPv6 architecture has led to the redesign of many aspects of network operations. One such design change involves neighbor discovery, which is itself now defined as a means for stateless address auto configuration, or SLAAC. So DHCP for IPv6 includes a number of design changes that include support for both SLAAC and stateful IPv6 addressing. So DHCP-v6 can support stateless and stateful addressing. Stateless, stateful. DHCP-v6 remains as a client-server base. Same thing with the DHCP. DHCP client, v6 client, requires IPv6 address. DHCP-v6 server assign IPv6 address. Client-server base. However, this includes a significant number of changes to align with the design aspect of IPv6. Okay. As such, DHCP-v6 stateful and stateless implementation and characteristics are explained. So for stateless, I already told you how it works. For now, in this topic, I will tell you how the stateful works. Okay, so I'll describe the feature of DHCP-v6 and also explain the stateful and stateless behavior of DHCP-v6, and we will configure a DHCP-v6 service in the ENSP. So again, client server-based service, DHCP-v6. So we still have a client. Oops, where's my pen? Okay. So client requests IPv6 address. Server assign IPv6 address. So this is a stateful address auto configuration, stateful. So this is UDP base between client and server. UDP base port number. The client side will use port number 546. The server side will use 547. Okay, means the DHCP-v6 message sent by client will be sourced from 546, destination 547. And the DHCP-v6 message sent by server will be sourced from 547, destination 546. So these two, please remember, must memorize this. Client 546, server 547. So how the stateful works? RA, router advertisement. Still remember that one? The router advertisement at, let's see, I will open this. Stateful addressing. No. Okay. This one. Router. Okay. This is what? This is a PC when a PC newly joined into the IPv6 network. Oh, so what happened? Don't know. So the first thing first, the PC will always send a router solicitations to find all routers, to find who is my gateway. Send router solicitation. Then the router will tell him what to do. The gateway, the router will send a RA, router advertisement, to tell the PC, okay, what you should do, what action should you take in this network. Okay, So there are two actions, two kind of actions. Okay, the PC will choose one. Actually, not the PC will choose one. The router will tell you, okay, you should do this, or you should do this. Means that the router will tell the PC to, you should do stateful address configuration, stateful, or you should do stateless. How the router tell the PC what to do, stateful or stateless, by using this. Inside the X-ray, it's the same thing. Router advertisement. There's a flag M and O. M means manage. O means other configurations. Okay. So when M equal to 1, O equal to 1, means that this network is a managed network, and you should get a IPv6 address from a DHCP v6 server, and also you should also get the other configurations from the DHCP v6 server. So when M equal to 1, O equal to 1, PC should do stateful addressing. Okay, where flags M and O are set to 1. Okay, so when M is 0, O is 1, means that this is a stateless. Okay, stateless addressing. So when M equal to 1, O always equal to 1. When M equal to 0, O can be equal to 1. Okay, so according, yes, for example here, now the client receive, okay, the client send a router solicitation. The router send reply with a router advertisement. Then the client read this, oh, M equal to 1, O equal to 1. So, okay, then the client, oh, in this network, I should do stateful addressing. So first thing first, I should look for my DHCP v6 server. So where is it? Look for the DHCP v6 server by using Multicast. Okay, link local address are used as source address by the client. Okay, DHCP server reached via the Multicast address FF02 :1:2. So this Multicast address means all DHCP relay agent and server. Means that the IPv6 client will use its own link local. This is the link local, self-generate. Okay, all the IPv6 devices will have their own link local address. Okay, so this is the source address, source IPv6 address, and then destination to this Multicast address. So send out to the network. Send. So look for is there any DHCP v6 server or the relay agent in this network? And if there is, let's see, the server will reply. So this is client, send from port UDP port 546 to port 547, solid sites. Okay, S. Okay, this S means the first one. Okay, this one. Okay, this is Multicast. Okay, Multicast, Unicast, Multicast, Unicast. Okay, so later we'll see we will run the ENSP to see all these 4 packets. So discovery of server and assignment of IPv6 address and configuration parameter rely on the set of 4 messages. Solicit, advertise, request, reply, then done. So server after, okay, again, so the same as the IPv4. After the client receive, okay, I received this IPv6 address from the server. Before I use this, I still have to do validation, either checking. So at here, the client will do, okay, duplicate address detection, DAD, to check. This is again same as the IPv4. IPv4, the PC will send a gratuitous ARP. IPv6, the PC will send the ICMP ICMP what? The type will be, let's see, the type will be 135. Okay, 135 is an ICMP type. So in IP, before you have ARP, in IPv6, no more ARP. So there are many functions that can be done by using the ICMP v6. So solicit, advertise, request, reply, SARRs. Okay, SARR. Okay, and then next one, if it is and if the manage m equal to 0, o equal to 1, the client know that okay, I should get other information from the server. Just get the information, and then server reply. Okay. So what the difference between this and this, stateful and stateless? Okay, the main difference is stateful. If stateful, the client will request the full 128 bits IPv6 address from the server. Means the client doesn't need to self-generate the EUI64. No. Even the prefix also not follow the prefix given by the gateway. No. You will follow the prefix, or you get the 128 bits, everything get from the server. If stateless, client will get the gateway, the prefix for the gateway, and then the EUI64 self-generate, and all the other information such as who is your DNS, what is your list time, and what is your NTP, or any other information get from the server. Okay, so different is how you get the, between stateless and stateful is how you get the IPv6 address. Okay, so and the thing is DUID, DHCP unique identifier. So unique identifier of clients and servers in the DHCP community. So parameters bound to each DUID using IA. So how to use this DUID? Each client or each server only have one DUID. So the server will use this DUID to identify who you are. This client, who you are, where are you from? So because the server needs to identify the DUID, based on DUID, then you can assign the IPv6 address. So the most important thing here is this. Enables just setting the DHCP DUID. The DUID IL format is assigned by default. Okay. So in VRP, or I should say in Huawei routers, we already support DUID LL and DUID LLT. Okay, or I should say Huawei router, Huawei switches. We already support DUID LL and DUID LLT. Okay, these two, only two formats, DUID LL, DUID LLT. So you must remember these two. Must memorize LL and LLT. These will come out in the exam. So next one. DHCP, the IPv6 address pool. So these are the configurations. So how to do it? You create a pool, DHCP pool. This is a command, and this is a name of the pool. It's a string. And then address, prefix. What is a prefix? 3000:/64. And then excluded address. Maybe this is the DNS server IPv6 address. So you put, oh, yeah, it is a DNS server. You can assign, okay, in this pool, in this DHCP service, I assign my DNS server is this. And the DNS domain name is this, Huawei.com. Next, okay, you created a pool, and then how you apply this? You're going to stay into DHCP, enable, go into the interface. This interface, and IPv6 enable, then only you can assign IPv6 address 3000:1/64. you can either use space 64 or /64. It workable, the command. And then you assign, okay, I want to use DHCP v6 server pool 1. Okay, means on this interface, the router will use the pool 1 IPv6 address assigned to the client. See, that's just a basic command for IPv6, DHCP v6. So you still can display the statistic, the status, display DHCP v6 pool. So in my pool 1, okay, pool 1, this is my address prefix, 2 in use, excluded address, DNS server address, domain name. Okay, so next. So which DUID formats are currently supported within VRP? Is the DUID-LL and DUID-LLT. And if the M and O bits of a router advertisement are set to 1, what actions is taken by the client? What actions? So the client will do this stateful addressing. Okay. Stateful IPv6 addressing. Okay, the complete term. Stateful IPv6 addressing. This one. Okay, so we go to do the EMSP. We try to do the capture the Wireshark between the PC1 and this router. HOI router can also be a DHCP v6 server. So PC1, right click, capture data E1. So it's empty, no traffic coming in or out. So DHCP, so here's the command, sysname DHCP. And then you have to put IPv6 system view, IPv6, enter. This purpose for you to enable all the DHCP IPv6 feature. Only you have to put this, then only you can start to configure any of the IPv6 features. Because this IPv6 is disabled by default. It's no IPv6. You cannot. So you have to put this. And then you say have to enable the DHCP feature. So I do this 3 first. Or I should just type this. So DHCP system view, sysname, DHCP server. Okay. So I put IPv6 enter. Then DHCP enable. Okay, so I want to configure DHCP v6 pool, DHCP v6 pool, question mark. Okay, a string, what's your name? I just can just put a pool 1. Okay, and then what is the prefix of my pool? Address, prefix, question mark. So you can put 2000 /64. Enter. So whether you do exclude address or not, that depends on you. So I better just follow, also can, excluded. Excluded address, question mark, okay, 2000 /1 space question mark. Okay, this address to what address? Or just if you want to exclude 1, just press enter. So and then quit, and then go to the interface G000 IPv6 enable. Then only you can assign IPv6 address. So I put 2000::1 /64. Enter. And then put DHCP v6. Yes.
After the sysname and the IPv6 has been enabled, why can't one say DHCP version 6 enabled?
Oh, it's included in the DHCP.
Yeah,
so DHCP,
I mean,
you don't have DHCP v6 enabled. Does you use the DHCP enable? Okay, that's a command.
So, yeah, because what I mean is, since we are looking at version 6, why is DHCP version 6 enable not used, for example? Is that by default?
This is what the command have.
Okay.
Okay.
Right.
So you can say that DHCP enable can be enabled for both DHCP v4 and v6. Okay.
Okay.
Okay. So DHCP v6 server pool 1. I want to use this pool. Okay, so let me try to display.
One more question, Mr. Bay.
Yes, sure. Yes.
So are we saying, for example, the excluded address command is in IPv6 is, say, equivalent to gateway list in IP version 4?
Again? Sorry?
Is there a relationship, say, in version 4, you say gateway list, you give the net address or IP address, and then here you're saying excluded address for version 6. Are we saying they're similar in terms of the various versions?
Yeah, yes, the same thing. Huh?
Oh.
Yeah. In DHCP before, it just exclude the IPv4 address. DHCP v6, you exclude the IPv6 address. Okay. So these are the command I can do. I display one in use. Okay, here I can see from this. Okay, so you always can see now the PC already configured to use a DHCP v6. So the PC will send a solicit. Okay, solicit. Okay, this is the Multicast. Okay, send from the link local address of the PC destination to Multicast. Look for all DHCP v6 relay agent or server. Okay, so next one, still solicit. This one advertise sent by the server to the PC advertise Unicast from link local to link local address. Then again, the client send multicast to the server, and then server reply Unicast. Request reply. Okay. So again, source port 547, destination 546. From server to client, server 546, client 54, server 547, client 546. From client to server, client 546, server 547. Okay. So after that, is ICMP v6.135, and try to look for, this is the solely cited node group, FF02:1:FF00:2. Okay. Options, this ICMP v6, neighbor solid citation 135, code 0. Okay. For the others, Also the same, neighbor solicitation 135. Okay. Solicitation, neighbor advertisement. Okay. Let me show you an example of the IPv6 header. You can see version 6, traffic class, flow label, payload length, next header, ICMP v6. Next header is ICMP v6. Okay, and the hop limit. Okay, 255. Source from link local address, destination also a link local address. Source MAC. Okay. So from this, because this is a self-generated, so from this, the router or the server, the router. Okay. Let's see. Looking for this. The router can note that okay, this is the, because this behind here is a USB 4. Based on this, the router also can backward to find out what is the MAC addresses. 5489. But here also already have a 5689. Okay. PV6. This one 5489. And this, okay. So the most important is this SARR. Okay. 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 So let me so this DHCP-v6 we already done, and now do you have any questions regarding this DHCP-v6?
Yeah, Mr. V.
Yes, please.
I'm just looking at the IP6 addressing multicast.
The IPv6 multicast.
Yeah, addressing multicast.
IPv6 multicast. This one. Okay.
Yeah,
Do you have any questions? Yes.
It's ending with 1 for all nodes and 2 for routers, right?
Yes. You're right.
So for
yes.
the Wireshark, after running it, I can see under the Internet Protocol version 6. I don't know why I'm seeing the source as 2 and the destination as 1, and the source is the PC, is the host. I thought that should have been 1, while the destination should have been 2. Or am I missing something?
What do you mean by
That's
PC?
2000 double full column 2 for the source is what I'm saying on the Wireshark. And then 2000 double full column 1 for the destination. And I was thinking that the destination was supposed to be the router, so that should have been 2, while the source is the host, that should have been 1, right?
Yes. So you mean this?
It's flipped on my own here.
It's why. Okay.
The source is the one with the 2, and then the destination is the one with the 1. So
you think the destination should be FS02::2, not FS02::1:2. Is it
right? So on my own Wireshark,
yeah.
I'm seeing the destination as 1 instead of 2, right? Since the destination from the source is the router, right?
Sorry, which message you mean? So
right. So the source here is showing 2000 double full column 2 for the source. While yours seems to
column.
be 1 there, isn't it?
Oops. Or do you mind to share your screen to me? Let me look at your screen.
Okay. Share my screen,
Okay.
right?
Yeah, share your screen. I will stop share.
Okay.
So please share your screen. Huh? Let us look together.
That should be the desktop, right?
Yeah, your desktop. Your screen one.
Screen 1. Oops, sorry. I'm coming. Just a minute.
Yes, yes, please. Take your time. Huh?
I should close. Can you see the screen?
Not yet. Maybe it takes some time to load. All right, you already click. You click on share screen, and then you click on screen one, and then you click share.
Okay, hold on. I'll soon be there. Share screen 1. Is it coming up?
Yes, I see it now. Okay, I see it. Okay, so you can continue. Show me. Okay.
So you can see this is what I'm talking about. The source is having 2, which is the host.
Oh, I see. Yes,
Destination
this is correct.
1.
This is correct.
So I thought the 2 should have been the router, right?
2 should have been the router. According to my configuration, the router is 2000::1. Colon 1 is the router. Colon 2 is the PC.
So it's correct?
Yeah, this is correct. Yeah, everything is working as expected. So you can try open your PC, the PC command prompt. I mean the ENSP. Inside your ENSP, you open the
Sorry,
PC.
carry on. I should share the screen.
Or you can stop. Okay, I know what you're talking about now. Okay. So let me further elaborate more. Okay. So my screen to share. Okay, this one. And then my Wireshark. Because I haven't do any ping request yet, yeah. Let's see. My PC1, I do IP config. What I have, IP config. So I have the IPv6 address 2000::2. Okay,
Yeah.
this is my game. This is what I have. So that's me. I ping.
Oh, okay. I see. Okay, I see. I was capturing the data at the router, not at the.
No, it's the same thing. Because everything you send is received at here. I will send, receive at here.
Okay.
Same thing. Either one. You will get the same result.
Okay. Okay, that's fine. That's okay. All right.
So I tell you ping should be, let's see, ping what? IP6 minus 6. So 2000::1. 8. Is it? It's wrong. Or can I just ping? 2000::1. Yes, can just ping. So now I get this. This is the ping I sent. Okay, ping request, ping reply, request reply. Okay. So in PC1, IP config. So how many IPv6 address I have? I have a link local, start with FEAT. I have a IPv6 address assigned by the DHCP v6 server, means the router. And I have two. Two. Actually, what other doesn't show here is include the solid cited node. Let's go into the router. Okay, in the router, okay, display IPv6 interface brief. Enter. And then you can see from this IPv6 address in G0, I have IPv6 address 2000:1. Okay, so yeah, I display IP interface brief. This is just for showing the IPv4, but I don't do any IPv4 here. Empty, not assigned. So if I want to check display interface G000, you also not see any of the IPv6. Display IPv6 interface G000. Okay, and then you will see this IPv6 is enabled. Link local. Please, you need to know how to read this. So this is I display the IPv6 status on the interface G0. So this is the So this is a link local address for the for the router, FEAT, and then global unicast, okay, and then this is the one. This is solid cited node group, join group. This router is joined into solid cited node group. And this router also in this group. Why is this? FS02::2 all router. This router also join into all nodes group. Okay, and this I have another solid cited node. This one is end with 00:1. This one is end with 521913. 521913 right here. 521913. So I have two solid cited node address. So and then this one is DHCP v6 server group. Okay.
Right.
Okay. So you must know how to read this. Okay. Because this also will be one. Yes.
Yeah, showing one on that. That's correct.
Yeah. One. Okay. So you must know how to read this because this will appear in the exam also. So if you know how to read this, this is link local, this is the global unicast. Maybe if it doesn't have global unicast, also can. You just have to read, know how to read this. Okay. So I think that's all. Okay. So let's try one more. Let's try to ping using the link local address. I can ping the link local address. Let me go to the DHCP server. I copy the link local. Here, I copy the server to the PC. Ping, paste, enter. Also can ping. But if you ping using the ping to the link local address, the request also sent out from the link local address. Link local address, then DHCPv6, the ICMPv6 header, so the same 255. Okay. Okay, so this is it. Okay. Okay, so again, in IPv6, so we have got no more no more network address translation in IPv6 because everyone will have a global unicast address, and all the devices will have global unicast address. So it means that for mine, for my office that here is our ISP will assign you the global unicast. Let me check. Let me show you. Let me show you. Okay. No, not this. So, what is my IP address? What is my IP address? Oh, so for mine, and here my ISP in my Malaysia is time.com, time.com. So and then this is my IP address 202.184.198.95. This is the IPv4 public IP assigned by my ISP to my, because I subscribe the package. So my ISP doesn't provide IPv6 address. Okay, let me see. Okay, there's no IPv6 address. What is it? Let me check. So, okay. So let me go to bgp.he.net. So I go to this website, bgp.he.net. Okay. And then let's look at my time. I'll just click on this AS9930. This is my ISP AS number. Okay, I can see the prefix B6. So you can see these are all the IPv6 address range held by my ISP. So 2001. You see, global unicast start with 2. Start with 2. Start with 2. Okay. So what else do you have? Nexus. Let's see. Nexus. This is another ISP. Okay, in Malaysia. Okay. So in Nexus also provide 202. Let's see what we have. Let's see MNT. We have this. Is it MNT? MTN, sorry, it's MTN. Okay, MTN. Okay, so this is the IP, the ISP in GU. So I should, which one should I pick? I just click on this. Net design. What is it? For this one, let me try. 9129. Prefix. Okay, only have one sub and one group, one range. V6. connected to, who is this? SA, Kenya. Okay. So
sorry,
this,
sir.
yes.
Which one did you click to get to the prefixes and yeah, to this interface, to this page?
This page. Okay. First, what you need to do is you go to this. You check what is my IP address in your google.com. You type what is my IP address.com, and then you will know who is your ISP. Yeah, ISP.
Okay.
So complete P detail. What do I have? Okay. Okay. So first you get to this page first.
Yeah.
Have you get to this page? Now can you see your public IP?
Yeah.
Then below here, show complete IP details.
Yeah.
Show complete. Okay. And then you see IP address, and then below here, ASN, the AS number of your ISP. Yeah. ASN 9930. Okay. For mine is 9930. For yours, what's yours number?
36873.
36873. So you go to this website. Okay. Oops. Should be bgp.he.net. Okay. bgp.he.net.
Yeah.
Okay, again, what is the number already? AS. Again, you repeat your AS number.
Yeah. 36873.
36873. 36873. I put AS 36873 search. Oops. So Airtel networks. Use from here you see the Airtel is the ISP. Airtel.
Okay.
Yours is Airtel, right?
Yeah, Airtel.
So this is what your ISP. Okay, this is what your ISP have. Like the graph V4. So your ISP is this one.
Yeah.
AS36873. So
yeah.
Your ISP is connected to another AS. These are neighbor. Exchange point of Nigeria. It can be a Bharti Airtel.
Bharti Airtel, yeah.
PCCW Global. Also this level 3 LLC, level 3 parent, LLC. Level 3 GTT, Orange SA. So these are the neighbor AS. Okay, connected. So you can look at the prefixes, the V4 prefix. So if you look at your IP address here, you should find the IP, the prefix somewhere here. Oh, so your IP address should be start with 105 and then 112. Yeah. 105, 112 somewhere inside this range. One of this range.
Yeah.
Okay. So these are the IP address owned by Airtel. So your ISP own this IPv4 addresses. These are public IP and can assign to the customer.
Right.
So then peer v4, these are the BGP peer of the Airtel. Okay, these are the BGP peer.
Okay.
Who is so Airtel doesn't own any IPv6 range, only v4. So no v6. Okay.
Yeah.
Next. Okay. So that's how you check your ISP. Okay. Okay, so I think that's all for this TCPv6. So now we're going to another IPv6 topic, which is the routing technologies. I close this one. I will show you another topology, which is OSPF v3. Okay, so I share the topologies to you. So here I'll start the topology. So please download and start on the device. So this one I can close this. Okay, this one. So this is a very simple topology. There's two routers, and then both this router will join become the OSPF v3 peer. Same, actually the concept is same like the OSPF v2. Both have to join, they have to become peer, become the neighbor. Okay, they have to become neighbor, and then they also run the elections to decide with DR and DDR, and also they advertise using the OSPF protocol packets, the hello packet database descriptions, LSR, LSU, LSX, same, it works the same thing. So but the OSPF v2 and v3 cannot compatible. You cannot say that R1 run OSPF v2, R2 run OSPF v3, then they can form neighbor. No such thing, cannot. Okay, so I start the device. Okay. Okay, so the device starting. Okay, let's minimize this and we go into the slides. So IPv6 routing technologies. So in IPv6, what are the routing technology we have? So we have the most famous is the OSPF3, and also we have RIP-NG, RIP next generation RIP-NG. So these are the distant vector. OSPF3 is link states. Okay, next. Okay, routing technology. So the changes to the address architecture have introduced the need for routing protocol that are capable of supporting IPv6. IPv6 routing protocol include OSPF v3. So the characteristic and operation of each OSPF v3 generally reflects those used in those in v2. However, contains some distinct differences that are required to be understood. Okay, so I will describe the characteristic and operation of OSPF v3, and then we configure the OSPF v3 routing protocols. So OSPF v3 updates are sent to the all SPF router address that is fs02::5. Okay, this seems very familiar. And open this. Is OSPF. Oops. Yes, it is OSPF v2. So this is what is this? Okay. Can I zoom in? Like this. Can I zoom in? It's not zoom in. Can you see this? 224.0.0.5 to all OSPF router. 224.0.0.6 to OSPF DI and BDI. So in OSPF v3 we have FS02 multicast FS02::5 is to all OSPF router, and then we have a FS02::6 to all DR and BDR in OSPF v3. So let's try to find out FS02::5. Should be 02, 02::5. So IPv6 multicast address space registry. So this is already an open standard. Okay. So I have not local, link local, not local, link local. Five and 6. So these two. Okay, OSPF IGP, OSPF IGP, DR, these two. FS02, ::, means on 0 and between 5, ::5 and ::6. Okay. Okay. And so link local, so same thing. Link local address used by default to define the next hop. Link local address. So what does this mean is, let's say for router A, let's say router A want to go to the loopback 0 of router B, this one. The next hop IP address, IPv6 address will be the link local address of router B. This is the next hop. They use link local address as a next hop. Means these are self-generated by the router because they are neighbors. Okay, they use this. Then for OSPF v3, how the router ID is being given. Okay, for router ID, it stays same as v2, 32 bits. Format 1.1.1, just like your IPv4 addresses. So because of this, the router ID cannot borrow from the interface anymore. It must be manually defined. Because your IPv6 address is 32 bits. Here, the router ID stay as still the same, 32 bits. So cannot borrow from your interface. So must manually define. And then router ID continues to support for DR and BDR elections. Okay. And then, so OSPF v3 pooling behavior. OSPF v3 operates on the principle of pooling as opposed to the per network or per subnet concept used in IPv4 pooling. So what does this mean by is this. In router A, let's say router A running OSPF-v3, how they form neighbor. Okay. They form by link, by using the link local address. Okay, as long as I connected to this network, I can form neighbor. Regardless, regardless what is my, let's say my global unicast or my IPv6 address, regardless, as long as, because inside the same network, they are using the link local address to form neighbor. Means that I can form neighbor to the broadcast network, the broadcast domain I connected to. I connect to this link. I connect to this network. Means I can form neighbor with B, C, and D. Okay, so I don't care whether we are in the same broadcast domain, because IPv6 don't have broadcast domain. So I don't care whether we have the same prefix or not, because it's actually we are using the same prefix here, because we are using link local, FEACT. Sure, we can form neighbor. And if we're using this link local address, because behind the last 64 bit is using the MAC address, so we confirm this link local, all this is unique. Okay, so next, in OSPF-v3, the authentication, no authentication field anymore. No authentication in OSPF-v3. Instead, relying on the AH and ESP extension header of IP for security. This is a basic IPv6 header, and then you can extension header AH and ESP, and then you have your OSPF-v3 header. So enabling the OSPF-v3, IPv6 still the same thing. You have to enable IPv6 first, then only you can configure OSPF-v3, and then you have to configure the router ID. You must configure router ID, and then how you doesn't create the area as here. You go into the physical interface, put the command IPv6 enable, then only you can assign IPv6 address. You can put FEACT link local, or just put auto link local, and then this is how you put the OSPF-v3. So OSPF-v3, okay, area OSPF-v3 process 1. This process 1 means this process 1. If you put this process 1, means the route this interface, the router will use this router ID 1111, and then area 0. Okay, and then IPv6 enable, IPv6 address for this loopback, and then you want to put this interface into which area? Okay, OSPF-v3 1 means this one. So also using the router ID 1111, including area 0. Here, OSPF-v3, you also can have, let's say, on this interface, put in area 1, area 0. Or for this loopback, I can put this in area 1, area 2, also can. Or I can put everyone in area 0. So just depend on what I put behind here, area. So it's for IP before OSPF-v2. How you put the interface into the area? You create the area 0, and then you put the network, you command network, and then put the network address. And then if you want to put this into the area 1, you create area 1, and then put this, assign the net, use the network command network, and then the network address of this network. So that's how you do it. See, these are the difference in command in or between V2 and V3. Okay, of course you can display the statistic, display OSPF at V3. So routing process V3 process 1 with ID 111. This is a router ID. So this is number of full neighbor 1. What is used to uniquely identify each neighboring node running OSPF V3? See the same as the V2 is the router ID. Okay, router ID is used to identify your neighbor. Who is my neighbor? Router ID. Okay. Okay, so let's go into the ESP. So these are the configuration I have prepared. So R1 will have a loopback interface 0. With this IPv6 address 2001:1:1:A. Okay, that's A because this is a hexadecimal A /64. R2 will loopback 0:2001:2:B/64. Okay, and then system for R1, system for R2. Both sides also enable IPv6. Both sides enable OSPF v3. And then send the router ID 1111 for router 2 2222. Both sides create the interface loopback 0. IPv6 enable. And then assign the IPv6 address. And then put this interface into OSPF v3 1 area 0. OSPF v3 1 area 0. And then on the physical interface G0, IPv6 enable. And put IPv6 address auto link local. IPv6 address auto link local. So you automatically generate a link local address. Start with FE80 and then end with the EUI64. And then I want to assign, put this interface into OSPF v3 process 1 area 0. OSPF v3 process 1 area 0. Means everyone is in area 0. So I just copy everything. I here copy R1, system view, enter, paste, enter. So let me put a capture data G0. Try to see the packets. Let's see, hello packet. Send to FS02::5. This is to all SPF router, Multicast. Okay, send by this R1 using the link local address. So it's the same. 0, 10, 20 every 10 seconds. Every 10 seconds. Same as V2 every 10 seconds. So the start first, header version 3, okay, V3. This hello packet. So this is the area ID is backbone area 0, backbone area. Hello interface ID 3, auto priority 1. Okay. So after that, now again still the same thing. After 40 seconds, router 1 assign itself as a DR 1111. Okay. Hello interval is still 10 seconds, router interval is still 40 seconds. So now DR, R1 is the DR. So we go onto the R2 side. Copy. System view, paste. Okay. Okay. So send by DXC is R1, for EBE is R2. Send a hello. Reply, send a hello. Active neighbor, form two-way and then form full. So again, still the same thing. You have DD. Okay, there's V3. Database description, you still have the link state request. Link state request, so many requests here. Okay, you still have the LS link state update, LS update, link state update, and then link state acknowledge. Still have this thing, okay, and it's how you form neighbor. Okay, this is your neighbor. Hello backend. Still every 10 seconds. So here R2 and R2 is quit. I try to display the statistic. Display OSPF V3 peer. Neighbor ID 111 is miss R1. My neighbor priority is 1. My neighbor miss R1. Router priority is 1 on this interface. So the neighbor between the neighbor status between R1 and R2 is full, and then the neighbor R1 is DR. That time countdown from 40. Interface G0. Okay, display OSPF v3. What I have display OSPF v3. Process 1 ID 2222. Then I should have display OSPF v3 peer. Okay, I have a question mark verbose. There's more things to see here. Verbose. So neighbor 111 is full. Interface address is this. This is the R1, and then in the area 0 via G0. The DR priority is 1. DR is 1111. BDR is 2222. Okay. Or I can put display OSPF3 peer G000. Still the same thing here. What do we have? I shall not verbose. Still show the same thing. Okay, same thing. So for now, display IPv6 routing table. For V4, just IP routing table. For V6, IPv6 routing table. So here I can find the interface to back, or I should find the destination. This is R1 to back. The destination, the next hop is the link local address of R1. This is the next hop. Interface going out from G0. Okay, protocol OSPF v3. Preference 10. Okay, v3, v2, v3, both are preference 10 by default. Okay. Okay. So that's all. So we can try to do some ping. R2, I want to ping, let's say, IP address. Copy. Try to ping question mark. What I have IPv6. Ping IPv6. Ping IPv6 paste this one. Yeah, success can ping. So below, okay. So I ping the loopback. Okay. So I'm also using a loopback to ping. Ping the loopback 2001118. Okay. So ping and reply. So the Ethernet 2 header still the same. IPv6 is changed. IPv6 header from V4 changed to V6, and then ICMP V6. Okay, this is how ICMP V6 looks like. The pin request is type 128 code 0. The reply is 129 code 0. Continue to hello bracket. Hello, okay, on hello every 10 seconds.
Sorry, Mr. B.
Yes.
You're thinking IPv6 what?
Again, by R2.
Ping. Oh, okay.
Is the loopback of R1.
Okay.
If I just put the pin and then paste, cannot, because you just put the pin, the router will thought that hey, this is a IPv4, but the router cannot recognize this IPv4 address. Okay, to put the ping IPv6. So the router know, oh, you are ping an IPv6 address.
Okay.
Yes.
Okay. Nice life.
Okay, good. So the same thing. From neighbor also the same. Okay. So that's all for this OSPF V3. So now we have completed all the IPv6 topic. So we still have the MPLS and the SR. Okay. Okay. So but for now, let's take a break. And try to digest what we have. I have two different models, but they provide the same speed.
Yes, possible.
Yes. So B is not correct. Is false. So only 3 answers. Oops, for this one. Okay. Where is it?
Sorry, Mr. B, I lost my network.
You lost your
Hello?
network? Hello, yes.
Yeah, I just came back. So what's the answer to that earlier one, right? C, D, and E only?
Yeah, C, D, and E only.
So that means B is not necessary. Okay.
Okay, so we go to the next one. So this is the diagram. Okay. So if the configuration of a port on a switch is as follows, the VLAN tag is strict when the port transmits the data frame of some VLANs. Which of the following is or are among these VLANs? When port, it means that interface G1, when this G1 send out from the port, send a data frames, he will strip some VLAN tags or some of the frames from some VLANs. Which VLAN are this? Which VLAN?
2 to 3, and then 3 to 100.
4 and 6.
4 and 6. Okay, based on the configuration, we can see untagged VLAN 4, 6. Yes, 4 and 6 is included. Any other VLAN? Do we have any other VLAN included?
1 is forwarding, right? By default?
Yes, 1 is untagged also by default. So 1, 4, 6. Okay, next. What is the total length of the VLAN frame defined by IEEE 802.1q? Total length of VLAN frame. Okay. VLAN frame, I think it should be mean VLAN tag. So, the VLAN tag. So, what is the size of one tag? 1, 2, or 3, 4 bytes? Only one answer.
4 bytes.
4 bytes, correct. Okay, next. Which of the following transmission modes requires clock synchronization between the two communication parties? You require clock synchronization. Select one.
Synchronous.
Synchronous transmission. Yes. Next. In Hoi devices, when NAPT, network address port translation, use a dynamic address pool, addresses in the pool can be used repeatedly. That is, one IP address can be mapped to multiple intranet IP addresses. True or false?
True.
True. Next, to establish multiple PPP point-to-point connections in the Ethernet network, a PPPoE server establishes connections with multiple PPPoE clients on one Ethernet port. How does PPPoE differentiate between each connection? Select one answer.
Establish multiple. Mark?
MAC address is included.
And session ID?
Session ID, correct. Okay, next. As shown in the following figure, which of the following is the authentication scope of the AH protocol in IPsec transport modes? So,
the AH?
Yes, AH in transport modes.
It has the...
How many header it cover?
It has the 3, I think.
3, is it?
AH. And the IP, I think. I think the IP is included. Or before.
3
or 4, I think.
Transport mode, AH, transport modes. Okay, wherever you see AH is all, everything. It's 4. When you see AH, either in transport mode or tunnel mode, everything.
Yeah, I wasn't sure of the IP included actually.
Yeah, okay, now you know. Huh? So these are the kind of questions will be asked for IPsec VPN. Okay. So which of the following authentication mode does or do not require a username and a password? Do not require a username and a password. Select one answer. Which authentication modes do not require username and password?
Local?
When you local, are you sure? Doesn't
Local.
require username and password.
I think A.
A, nah, nothing. Okay.
A.
A, yes, A, yeah. Correct. For all these Multicast, radius, and local,
Yeah, I remember local.
is
Yeah.
for you. You will need to define the username and password.
Yeah.
Okay. So this one. Okay. 15. If the packet matches the denied route in the ACL, the packet is discarded.
Yeah. True.
Correct. True. So very easy question. This one. Yes. This kind of question will be in the exam. Okay. Another scope. So this sign is IPsec tunnel modes. Which of the following is ESP encryption scope? Okay, remember ESP can do authentication and encryptions. But now in tunnel mode, what is the encryption scope of ESP? Tunnel mode. Two. Encryption.
Yes, 201.
Okay, 201.
4. It's 2.
Okay. It cannot be 4. It cannot be 4.
Yes. Yes.
Okay, if you encrypt
But I
your
know 3 is AHA.
you encrypt your outer IP header, how can the packet being forwarded if they don't understand the IP address?
3 is on AH-ESP mode.
It's AH.
3 is AH-ESP mode. So I don't think 3 should be correct. So I think 1.
Yes, it's 1. It's 1. You cannot encrypt the ESP header.
Yeah.
Because otherwise, it doesn't understand what is this.
Yeah.
What is the packet? So you need to leave the ESP header. But behind, everything is encrypted. Okay, 1. Okay, next. SNP v1 defines 5 protocol operations. True or false?
True.
True. True. Next. As shown in the following figure, which position should the AH header in IPsec transmission mode be inserted into? Transmission mode means transport mode. AH transport mode. So AH transport mode.
2.
Yes, 2. 2. So it doesn't cover the IP header. Just okay. 2 data TCP header. Yes.
Did you say we have 5 operations?
5 operation V1. 5 operation. Let me show you.
For the SNMP.
SNP V1. Okay, let me show you. Oops. This one. 1, 2, 3, 4, 5.
Okay. So there's setting and getting, okay.
Yes. Okay, these are
It
the 5.
was all looking like response request. So I was initially assuming it's the same thing.
Yeah, this okay, respond, get respond. The same thing, huh?
Yeah.
Okay. 5. And 19. Which of the following statements may be the cause of the failure to establish an OSPF v3 adjacency? One or more. Which one may be the cause of the failure? Okay.
Can the router IDs conflict?
Other conflict, yes. Router ID must be different.
The area
different.
They communicate by halo packets. So if the intervals are different.
Yes, they must have the same hello packet timer. Both sides, if both sides 10 must be 10 seconds. If both sides must be the same. How about this? IPv6 address prefixes of the interface are different.
I don't think it's necessary, is it? I don't think.
Not necessary, yes. Okay. Because they formed by using the link local address.
Yeah, link local.
Okay, this one. Sorry, cited node. Which of the following IPv6 addresses correspond to the solicited node multicast address of FS02:1:FFAB::FECA? Session being translated. No, stop. Never mind.
Solicited. Solicited.
Yeah, solicited. This is the solicited multicast address. So which of the following, one or more, correspond to this?
Solicited will get the
Which of these IPv6 address, which of these will use this solicited node multicast address?
It's C.
C is
F
included.
Yeah.
A.
It's C. It's C.
Nada es eso.
So the prefix that is the difference there, right?
So any answer else? These two are correct. Look at the answer. The first here is the multicast, the prefix for the solicited node. The behind ABFECA is the taken from the IPv6 addresses of the host.
That's the 24-bit, right?
Yes, 24-bit. ABFECA.
Yeah.
4 times 6. Okay, 24. So for all the address, you see AB:FECA is the answer. ABFECA include this.
D.
Yes. Okay. 3 answer. Next, if the value of the M and O flags in the router advertisement packet sent by the TCP/v6 server are 0 and 1, respectively, which are the following modes? Stateless. So DHCP v6 stateless. Auto configuration. Next, which of the following option is the simplest form of the IPv6 address? This one. Oops.
D.
D. Yes, it's D. Okay, so this need to be erased, needs to be removed. So only B and D, and then next. So they are the zero. So double colon, this remove the heading 0, 3, 4, 6. So this 3, 4, 6, this 0, 3, 4, 6, not the simplest yet. So this 3, 4, 6. Okay, D. Next, the solid-sided node multicast address consists of the prefix FF02 : 1 : FF00 : 0/104 and the last 24 bits of the corresponding unicast address.
B. Yes.
True,
The last 24 bits are the Unicast.
Yeah.
Yeah.
Correct. So next, okay, these two are questions. We haven't go through yet. These are MPLS and the SR. Okay, later we come into this. Now, so now we go into the MPLS. Okay. MPLS basic principle. So this course, this topic will introduce the MPLS architecture that contains two planes. Okay. Okay. So MPLS encapsulation mode and label formats. Two planes. What do we have? We discuss about two planes, encapsulation mode, and the label format. Three things. And the process of MPLS data forwarding is a key point of the course. So for this topic, you must understand how the MPLS data forwarding works, the process. Okay. So I will describe the background and typical application of MPLS, and then the basic concept and working principle of MPLS, and also I describe the process of MPLS data forwarding. So this is the main key point. How MPLS do data forwarding. Okay, overview. So traditional IP forwarding. Okay, before this, what is MPLS? MPLS. Okay, the full name, multi-protocol label switching. Okay, multi-protocol label switching, MPLS. Okay, you can see label. What is my label? Okay, traditional IP forwarding. Okay, this traditional IP forwarding is what we learned from first day until now. Okay, means how the router forwards the packet. Example, router A. Router A receive a packet. Router A check the destination IP address 10.2.0.1.
Hello, please.
And then
The meaning of MPLS again.
the meaning of the MPLS is in the, you can just Google, Google MPLS, Google the MPLS, you will see multi-protocol label switching. Okay, so router A sees the destination IP address 10.2.0.1. The router A will look through go through the FIB, the forwarding information base, from top to down. Okay, 10.0.1, 10.1.0.0. Okay, does it not match? The first 24 bit is the first 24 bit is 10.1.0. So 10.2.0 not match. So I should find any one 10.2.0 from top to down. Or this 10.2.0 match this. Okay, then I know my next one is 10.1.1.2. So forward to 10.1.1.2. Automatically check destination 10.2.0.1. Also check from top to down. Okay, this one. Forward to next hop 10.1.1.6. Automatically also check from top to down 10.2.0.0. Okay, 10.1.1.10. 10.1.1.10 forwards. The router D also check from top to down. Okay, this one. Next up 10.2.0.2. 10.2.0.2 means the direct connected network send to the destination. So traditional IP using the internet is the cost is low cost, but the switching efficiency is very slow. Why? Because the router need to check from top to down. Every time you receive a packet, you need to check the destination IP packet and compare from top to down. Compare until the last one. Until it found. This is just 1, 2, 3, 4, 5, 6, 7. Just 7 destinations, just 7 routes right here. So, but imagine in ISP networks, ISP router, we don't have just 7 routes, with thousands of routes. So the router need to go through so many routes, compare one by one every time. So this is a cost, because the router also need to calculate, take this, compare with this, need to do calculations for everyone. Okay, you will consume the CPU processing, okay, and slow down the time from the router receive the packet and forward the packet. The time taken between will be much longer. So mean the switching efficiency is very low. So, but the cost of this technology using the internet, traditional IP forwarding, the costing is low. Okay, but the switching efficiency is also low. So, ATM, there's another technology. Asynchronous transfer modes. This is a ATM switch. So for ATM switch, they are using label forwarding. So when the switch look at the ports, when the packet coming in from port 1, okay, coming at port 1, and then the label is 4/55. So straight send out to port 3 with label X/62. So the router, the switch, the ATM switch, doesn't even look at the IP address. They just see what the label coming in and send out to what label, just that. So this switching efficiency is fast, but the cost is very high. So in order to increase the switching efficiency of the Ethernet, okay, so we use this. We introduce the MPLS technology, multi-protocol label switching, label forwarding. So in this MPLS, MPLS domain. In this domain means that all the router in this domain run MPLS. So MPLS, actually we are mostly only ISP run the MPLS. The routers on the customer doesn't understand MPLS. Okay, so how it works? So I say green color is the MPLS header, white color is data, then IP header. Okay. So data and then the IP header. This is the normal IP packet we learned from the first day until now. So the router from the customer send a IP packet. Send to router A. Router is the PE, provider edge. So, or this also we call the ingress router, because this is where the packet coming in to the MPLS domain. So router A receive, check the destination IP address, and then router A found that, oh, this destination IP address I need to put into the push a label. I need to do label switching. label forwarding. So to do label forwarding, you must push a label 1024. Okay, add a label, the action we call push. Okay, push. And then next hop send to router B. Router B receive a packet, a label packet with label 1024 coming in. 1024, swap the label to 1029. Again, just now I say push. And then now swap the label to 1029, send to router C. Router C swap the label to 1039, send to router D. Okay, now router D is another edge. It's an egress router, egress node. Means the packet is leaving the MPLS domain. So this label packet need to forward to the customer, but customer doesn't understand the label packet. So router D have to pop the label and then check the destination IP address, and then forward to the customer. Okay, along the way, you'll notice router A will read the destination IP and push the label. But router B never read the IP header. It just read the label and then swap the label to 1029 and send. Router C also never read the IP header. Okay, router C just read the label and then swap to 1039 and then forward to router D. Router D read the label 1039, pop the label, and then read the destination IP address and send. So this router we are called the label switch router. Okay, label switch router because they swap the label. So between end to end, this one we call edge router, label edge router, because this is where the packet coming in and this is where the packet going out from the MPLS domain.
Sorry, Mr. Bay.
Yes.
Mr. Bay.
Yes, please. Yes?
I can understand the IP addressing between A and B. Hello, can you hear me?
Yes, I can hear you.
But
yes.
I'm a bit confused when it goes further, because if you look at the network there, it says
no. For router A to go to router B, router A forward this packet, this label packet based on the label. It doesn't look at the IP header anymore. Router A doesn't read the destination. Okay, when the packet coming in, the router A read the destination IP address. Okay.
Right.
Okay, according to this destination IP address, and according to the MPLS configurations,
right,
this IP packet need to be push a label. Okay, and then based on this label, this packet need to be forward to this next hop, router B.
No, I understand what you mean. I mean, we're looking at the MPLS here using the label switching. I understand that, but as it is now,
sorry, Dr. Bala? Which part you don't understand? Can you repeat again?
so if it's .4, then how do you reconcile .5 and .6 here? That's my problem. I was thinking that maybe the network should have been changing. So 10.1.1, then 10.1.2, and 10.1.3, and then we can be able to assign a .5 and .6 in this case, right?
Oh, you mean?
Yeah, I mean between the networks.
Which one?
Yeah, between the networks. I was thinking that normally it should have been, say, maybe 10.1.1.0, that's fine. 10.1.2.0, that's. I was thinking it should have been that, and each of the interfaces can have their own host IP
Network.
like.
You mean here is 10.1.1. Why here is also 10.1.1, and here also 10.1.1?
So, it's all right.
Why?
Let's make progress.
Okay, why? Because this is a network bits 30.
Yes. So we have only two, isn't it?
30.
Two hosts.
If this is 30, then the network address is 10.1.1.0. And then 30 means you have two host bit only.
It's already .5 and the other.
You have 4 IP address. You have 4 IP address in this network.
So one is
dot
broadcast,
0,
one is
dot 1, dot 2, dot 3 is the broadcast address. And then you go to dot 4. Dot 4 is the network address.
Yes.
Dot 4 is the network address. Dot 5 and dot 6 is the host IP. Then dot 6 is the, and then dot 7 is the broadcast address.
Okay. Correct. I've seen the problem.
Yeah, because of this.
I understand now. Yeah.
Because between router to router is one broadcast domain. We don't need to put the subnet to /24. No need, because we only need 2 IP address.
Yeah.
If not, you put /24, a lot of IP will be wasted.
Yeah.
Okay, so
it's okay. I've understood. Understand.
Okay, good. Okay, let's continue. So you understand the router B doesn't read when the router B receives the label packet, the first thing you read is the label. You read the label first. So, according to the router B, according to the configuration, if I see this label, then I sort to this label. So I doesn't need to read the IP header. Okay. So
Mr. B, sorry.
Yes.
When swapping the labels, is it automatic or is it manual?
Swap is because of the configurations.
Configurations.
Okay. Because of the configurations.
Okay.
Okay. So MPLS VPN. So this MPLS, this is a basic MPLS label forwarding. And MPLS, we also can use to do some other applications, like MPLS VPN. So what's the MPLS VPN? As for the virtual private network. So yesterday we go through the IPsec VPN and GRE VPN. So for IPsec VPN and GRE VPN, that's configured on CE to CE, customer edge to customer edge. Okay. For MPLS VPN, it's configured by provider to provider. The customer side doesn't need to do anything. The VPN is maintained by the provider. If IPsec, the VPN is maintained by the customer. So MPLS VPN actually need to subscribe. Need to pay money to the provider to maintain the VPN for you. If CE is the IPsec, CE to CE, maintained by the customer side own engineer. So it's free. Means you have to pay your engineer to maintain the VPN. So it depends. You want your own engineer to maintain the VPN, or you want the provider to maintain the VPN. Your provider maintain the VPN means that if your VPN is down, you just have to log a case to tell your provider check the VPN. If you're maintained by the if you are using IPsec VPN maintained by your own engineer, if your IP VPN is down, you have to ask your engineer to check. Okay, these are just the difference. Who manage the VPN? Okay, and also MPLS TE, traffic engineering TE. Another scenario we can use the MPLS. Okay, so in this, the concept up here is if following this, you see OSPF. If following the OSPF, this is GE, this is FE port. So this is 1 gigabit, this is 100 meg. So according to the OSPF, this is the lower cost path. Okay, so for all the traffic that come to router B, he will forward to this path. Okay, yeah. Traffic from network B also going to go to router B also forward to this path. But this is the best. Means the path below is the that's a backup path. Means it's not utilized at all, not using at all. So what happened? If in this kind of situation, if router B doesn't router B just know that this path is the best, lowest cost. So all the traffic is forward to this path, even when the port, the link is congested. But this is still the lowest cost because this is GE, this is FE. So I still forward through this path, don't care. Means that OSPF doesn't know how to do traffic engineering. He cannot say, okay, if for traffic engineering MPLS, I can separate, okay, this path, 70% traffic go to this path, 30% go to this path. You apply MPLS TE, we can do this, traffic engineering. Okay. Next. So, MPLS control plane and forwarding plane. Again, MPLS network model. So, this is LER, label edge router. Okay, and then in between all these are label switch router, LSR. And then what is label switch path? It's a path. This is a label switch path where the router A, if the router A sees a destination IP address, it will push a label. Push a label, and this packet will be forwarded using the same path to router B, to router C, to router D. This is the label switch path. Okay, means that if I want to forward this, forward this packet to this destination, follow this label switch path, which is from router A to router D. Router A to router B to router C to router D. This is the path need to be taken. So this means by the label switch path. Okay, and then MPLS control plane and forwarding plane. Okay, you can still remember, I tell you the control plane is where your routing table is. And then your routing table, you will download the best path. All the best path we download to the FIB. IP forwarding table is FIB, forwarding information base. And then all your IP packet coming in will be forwarded to the IP forwarding table to look for the best path. Look for the not the best, because all the path in the IP forwarding table is the best. So you look for the destination network and look for the next hop and send out. But now we add in the labels. We have to do MPLS. So IP routing table will download your routes to the LDP, label distribution protocol. So label distribution protocol, we give the label for according to the networks. On the destination network, they will have a label. So label, all this label will be forwarded to the label forwarding table. Download to label forwarding table. So in your data plane, you have one IP forwarding table and label forwarding table. So when there's a label packet coming in, it will be sent to the label forwarding table and look for the Okay, where incoming what label and then going out what label. Okay, this is incoming what label, going out still a label. This is done by the label switch router. Yes, label switch router. They change the label, they swap the label, And for this, when coming in IP packet, going out label packet, this is the label ingress, label H router, ingress. Label H router do this for ingress direction, ingress. Okay, when the label packet coming in as a label packet, going out as a IP packet. This is pop the label. This is done by also the label H router on egress when the label packet want to exit the MPLS domain. So egress. Okay. Next, label MPLS label format. So how the label looks like. So frame mode and cell mode. ATM use cell modes. And then Ethernet and PPP use encapsulation mode. Okay, so we just talk about the Ethernet and PPP and encapsulation mode. So this is your normal layer 2 frame. You have a payload, IP header, and the Ethernet header. And then the MPLS is added in between here. This is your MPLS header. Okay. Okay, means your router read the Ethernet header, then he will read the MPLS header. And then he will never either might not read the IP header. So depends on the actions of the it will be carried out based on the MPLS header. Next, so this is the MPLS header. The size 32 bit, 4 bytes. Remember this 4 byte, 32 bits. And then the first 20 bits is the label. It's the label. And then the next 3 bit is the XP, experimental use. Actually, this means the QoS. Okay, 0 until 7. Okay, 0 is best effort, 7 is the most urgent. Okay, stack label, bottom of stack is a flag, either 0 or 1. It's a flag. If this is 0, means that this label is not the last label in the frame. If this is 1, means that this label is the last label. Okay, and then TTL, same as the IP, okay, IP header, 255. Okay, 8 bits, 255. So what do you mean by why there's a stack? Last label or not the last? Okay, this is the what I mean. Label nesting. That's why you only see 1 label. You also can have 1, 2, and 3. 1 or 2 or 3 MPLS label in 1 frame. Okay, for different purpose, you will use how many number of label will be used will be different. So for normal, just a normal label forwarding, just 1 label. If you want to do MPLS, VPN, or TE, you have more label, 2 or 3 label. Okay. Okay, so means that this is a label 1. You have the bottom of stack 0, means that there is 1 more label. Next one. So this one also the bottom of stack is 0, means there is 1 more label. Next, so the third label s equal to 1 means this is the bottom of the stack, the last label. Okay, no more. Maximum only 3. Okay. So PID indicate the types of packets, follows and frame header. So this is a frame header. PID. Okay. If in the Ethernet, this means The next one is the IPv4 internet. 8100 means the IPv4. It shows the internet, the ether type. So 8847, this is Unicast. Maybe it's a Unicast MPLS packet. If it is 8848, means that this might be a multicast MPLS packet. So this is the PID on the frame header. If Ethernet, this is ether type, and then this is a PPP type in the PPP header. So this should be, when this is the PPP header, PPP, not Ethernet. You look at this. Okay, and then the forwarding process. Okay, so FEC and NHRFP. And FEC, forwarding equivalent cast, is a set of data flow with certain common characteristics. These data flows are processed by the LSR, label switch router, in the same way during the forwarding process. So FEC can be classified based on the address, service type, and QoS. So the most common one is the address, what we learned just now, label forwarding. So it means that all the packets, IP packets, with the same network address or with the same IP, destination IP address, will be forwarded using the same way. Okay, same way, same route. It's the same route. Okay. And then NHRFP is used for label forwarding. It contains the following basic information. What is the next hop of the packet? How to perform a tag operation? Either push a new tag, pop a new tag, or pop the tag or swap the tag. Okay, push, pop, swap. And then also may contain another information such as link layer encapsulation is for sending packet. So most important is who is your next hop and your label operation. Okay, so next, so this is the FEC. FEC also can mean your destination network. Okay, this is FEC. See, FEC. Okay, if the FEC is 10.2.0.0/24, okay, what are the actions to be taken? Follow the NHRFP. So you need to, if your next hop will be 10.1.2, and then your output interface is 0.0. Label operation is a push. Your incoming label, in label is now, no label. Out label, 1030. Yeah, it's the next one. This is the FEC of router A. If a router A see this, 10.2.0, this is the next hop. 10.1.2. Output interface S0. Label operation push the label 1030. Okay, and then send to router B. Okay. Oops. Next, is it? Okay. So this is a label. So router A push a label 1030 forward to router B. Router B check the label. Okay, incoming in label here, in label 1030. So I should swap to 1030. Yes, it can. Swap to the same label, also called a swap. And then next hop, 10.1.6, output interface S3. Okay, S3, send to S3. Okay. So for router C, okay, router C already received this, send to same as swap to 1032. Forward to router D. Router D received the incoming label 1032. Pop the label. Next hop 10.2.0.2. I need to read the destination IP. Send to that's the destination, the host. Okay, that's all. So which field in the MPLS header is used to identify the stack bottom label? Is the S, stack bottom. And which of the following actions can be performed when packets are forwarded based on MPLS label? Only 3 actions, push,
A.
pop, swap.
Pop, swap.
Only these 3. You must remember these 3. Not switch. This is the answer. This question always appear in the exam. Push, pop, swap. You remember these 3, you get the answer. You get the question. And this is a multiple choice. Means the marks for multiple choice is higher than true or false, and the objective select one answer. Okay, multiple choice answer, the mark will be higher. So make sure you get this right. Push, pop, swap. Okay, that's all for MPLS. Okay, let's take a 5 minutes break. 5 minutes break, and then we will go into the last topic. Okay, so welcome back. So this is the last topic of the training. So this is SR, segment routing. Okay, so we will learn about the some basic principle. So same as just now the MPLS, we will just learn about the basic principle, how it works. Okay, but we won't go through how to do the configuration. No. Okay, just learn the basic principle. So as a key technology of SDN, segment routing is also a key technology for simplified protocols advocated by IP networks. And it is widely used in IP networks. So this course or this topic will analyze the SR technology. So I will describe what is the advantages of SR and some basic concept and working principle of SR. So some SR technical background. So why we want to introduce the SR technology, because maybe previous there exist some challenges faced by existing technologies such as LDP. LDP is a label distribution protocol. This is what you see in the MPLS. So this LDP, it depends on the IGP such as OSPF or ISIS, and use a local label switching to support ECMP. ECMP means equal cost multipath. So what are these advantages of this LDPs? It has 11 types of protocol packet. 11 types. OSPF has 5 types. This LDP has 11 types. And this greatly increases the link bandwidth consumption and device CPU usage. Okay, this is a problem. And also, LDP only support the shortest IGP path for path calculation. It cannot support TE, traffic engineering. Okay. We support the lowest cost. Okay. So another technology, existing technology, is which you call resource reservation protocol. Okay. Again, this protocol is the challenges is configuration is complex. Complex ECMP implementation, 8 types of protocol packet to occupy network bandwidth and CPU processing. Okay, these are the challenges. And also, same thing. Okay, complex in ECMP configurations needs to be configured with multiple tunnel, huge workloads. Okay, to configure and maintenance. Okay. So these are the some challenges faced by LDP and the ISVP. That's why we introduce SR. Okay. And then from traditional networks, this is what we learn. Okay. One router will have its own control plane and forwarding plane. Means that router will have its own IP routing table and also the FIB, the forwarding information base. Okay, so the router, just like 3 routers running OSPF, they decide their own best path and then they forward it to the forwarding. They download the best path to the FIB. So the protocol evolution is slow if using traditional network. It takes several years from equipment submission, requirement submission to version release. So the OPEX increases linearly with the scale. Okay, lack of flexible deployment and use modes cannot meet service provider requirement for fast network service deployment. So slow deployment like this, traditional. So improve. We improve. We add a controller. So control is like the brain of the routers, all the devices. So all the devices, all the router now, they cannot decide their own best path. Everything they have to follow what the controller say. Controller holds the power, holds the authority to decide the best path, the control plane. So the controller decide the best path and tell, okay, this router, you follow this You follow this and you follow this. I send. The controller will tell all the router how they should forward the packets. The router cannot decide, cannot do calculation on their own. So network fault cannot be rectified only when the controller is faulty. The reliability is poor. It means that because only the controller can change the forwarding information base, change the best part. So if the controller is down and there is some changes to the network topology, okay, if the controller is down, nobody to change, nobody to can update the router what to do. So the reliability is poor. And the number of flow table on the large scale network is large. And the flow table delivery rate has a performance bottlenecks, and it is a subversion of traditional network and is not supported by equipment vendors and carriers. Okay, so maybe controller, if you will use the brand, according to, you must use the same controller, same brand. Maybe the whole set, the whole equipment, you must use from the same vendor. Okay, cannot mix. This is what we facing now. But if we use segment routing, it's different. Actually, what we want to improve is this, to improve the solve the single point failure. Okay. In segment routing, the existing protocol can be expanded to achieve better, smooth evolution. That can provide a balance between centralized control and distributed deployment. Okay, what do we mean by this? Controller also can do some calculations and update to all the router, telling them how you should forward the packet. And on some circumstances, on some situations, the router also being allowed to decide some of their own best part, because they also have some of the authority. Some of the authority, they can make some decisions. So some decisions they can make their own. Some decisions must follow the controller. This uses source routing technology to provide fast interaction between the network and upper layer applications. Okay, so these are the answers. These three answers will appear in the exam. So you memorize these three. Okay, these are the three answers. Also, this is a multiple choice questions. Higher marks if you get it right. Next, so SR background, SR technical framework. SR is a technical solution of packet forwarding provided by adding a series of segment identifier to a packet only on the source. Okay, what do we mean by this? It's a solution for packet forwarding. Okay, still it's a technology for packet forwarding. How they forward the packet? They will add a series of segment identifier, SID. SID means a label. Okay, so in LPLS we call that label. In SR we call this SID. So from now I will just use the word SID. But you have to aware that this just means the label. Okay, the label. So adding a series of SID to a packet only on the source means the ingress router will add the label on the packet. Okay, so the source node has all information about the path, forwarding path, and is better used for path control. Okay, segment list. So the IGP, BGP is extended to support segmentation, communication with the controller, collect topology, program path, and device information. So we have the SDN controller using BGP, TCP, and netconfig. Okay, and this data plane. Okay, path selection is the same. Shortest path tree configuration and also explicit path based on the segment list. Okay, path selection. Go to this. Segment list, go to this. Okay. And then this, after this, okay, data plane, data plane, MPS forwarding, label forwarding, smooth evolution on the line, like a segment label. Okay, data plane, you have the label forwarding. Because the segment label is also same, more or less, actually it's the same concept with the MPLS. Still a label forwarding, and this is IPv6. So IPv6 will use a segment routing header. It's an extension header, one of the extension header. Actually, it's a new type of extension header. Okay, this is for IPv4, IPv6. Okay, so in control plane, again, control plane, router can do its own decision, some of the decision based on the ISIS, OSPF, or BGP. And also, he also might need to follow the instruction given by the controller. Okay. Next. So basic concept of SR. So basic concept of SR, segment routing domain means that in the domain, all the routers are running segment routing. Okay, SR nodes. Segment is an instruction that node executes, means the instruction the segment on an ingress packets. Means the IP packet coming in. Okay, what the router need to do. So, for example, forwarding a packet to a destination according to the shortest path, or forwarding a packet by using the designated interface, or forwarding a packet to a specific application or service instance. Means the instruction what to do. Okay, when the router with running with the segment routing, it receive a packet coming in. What to do? It can be actually it can be a edge router, or it can be a label switch router in the middle. Also can. So thus, this is just a instruction what to do. And SID, segment ID, segment routing, define the destination address prefix, node and adjacency on the network as a segment and assign segment ID to this destination. Nodes and adjacency, the segment ID is equivalent to the MPLS label in the traditional MPLS technology and is mapped to the MPLS label at the forwarding plane. Okay, in MPLS, we give the destination network with a label. In SID, we give a label on the destination address on the router, the node, and even the link, the path. The link also give a ID. We got so many labels to use. 3 types of label in segment routing. And then sRGB is a segment routing global block local set tags. It's a local tag, local label set reserved for global segment. In MPLS, sRGB is a set of local label reserved for global label. Okay, in IPv6, sRGB is a set of IPv6 addresses that have not been used globally. Okay, later we are going, I will explain again what is a sRGB in the slide behind. So segment list is just a list of SID. Segment list, a list of SID. So a list of instruction. That means a list of instructions. Okay. So segment routing. Basic concept of SR is to divide the network into different segments and then combine them to guide the packet forwarding based on the specific path. So segment ID identify the unique segment on the forwarding plane. MPLS label are mapped. Okay, 3 basic segments: adjacent, forward drop, and node. Okay, so here is this adjacency segments, prefix segment, and node segment. So adjacent segment is automatically allocated, dynamic. Prefix and node segment is manually configured, and adjacency SID is outside the sRGB range. Prefix segment is inside the offset value of the sRGB. And then prefix segment is the prefix ID of the nodes. Okay, what does this mean? The adjacency segment means the label of the link, the path, the link. And then prefix ID means the label for the network. For this network, I have a label 100. For this path, 1001, 1002, 1003. Okay, and then node ID means the router itself. This router, node ID 101. This router 102. This router 103. Okay. For the path, the network, and the router. 3 kind of SID. So how they use? See, prefix segment. The router means the router. Label the router. Based on prefix segment, IGP use the SPI algorithm to calculate the shortest path, which is called the SRBE, segment routing best effort. As shown in the following figure, node Z is the destination. This is node Z. And destination node and its prefix SID is 100. So 100. After IGP flooding is enabled, all devices in the IGP area learn the prefix SID of PE2 and then use the SPI algorithm to obtain the shortest path to PE2. Okay. So what do we mean by here? You see this router. This is a packet coming in, a normal packet. This packet push a label. Or I should say push the SID. Push the SID 2100. Okay. What does this 2100 means? Well, this packet, because of this P1. Okay. 2100. Okay, let's start from the PE2. The PE2 tell the P5. If you want to go to this network, please give me a label 1100. P5 tell P3. If you want to go to this network, give me this label 2100. Router P3 tell P1. If you want to go to this prefix 100, this network, give me a label 3100. P1 tell P1. If you want to go to this network, give me a label 2100. So when the P1 receives this packet, look at the destination IP address. Oh, I need to go to this. So according to my configurations, I have to push a label or push a SID 2100 over to P1 because this path, the cost is 1, cost 1 means 4. And then this is 2, 2, 2, 2. 4 times 2, 8. So this is the best path. So the router decides his own best path and put in the SID. So this is forward to P1, P1 see, okay, 2100. So I see 2100, I swap to 3100. Forward to P3. P3, see, 3100. Swap to 2100, forward to P5. P5, see, 2100, swap to 1100, forward to PE2. PE2, see, 1100, okay, port the label, send to destination. So this is best effort. Means this router decide that this is the best path. This router decide this is the best path. This router decide this is the best path. This router decide this is the best path. Each router decide their own best path. So this is we call segment routing best effort, SRBE. So this is done just by using the prefix SID. Okay. So segment, adjacency segment. Now we are using the path, the label, the SID of the path. Okay, based on the adjacency segment, the head nodes, the first one, the head nodes, specify a strict explicit path, strict explicit. In this manner, path adjustment and traffic adjustment can be performed in a centralized manner, so that SDN networking can be better implemented. The adjacency segment is mainly used for traffic engineering. Okay, this is what we call SRTE, segment routing traffic engineering. Strict, explicit, strict, must follow exactly. Okay, this is just by using the adjacency segment ID. How do we mean by this is, okay, the P1, when the P1 receives this packet, okay, according to the decision made by the controller tell P1, okay, if you want to go to this destination, put all this label, stack 1, 2, 3, 4, 5. This 5 label on the packet. Okay, this 5 label, and then okay, PE1, okay, PE1 follow the instructions, stack this 5 label on the packet, and then the PE1 read the first one. 102, okay. I what? Discard. I pop the label, and then send through the path 102. Okay. P1 read the first one, the first label, or the first SID. 204 means this path. Pop, then forward. P3 see, okay, 405 is this path. So pop the label, send to P4. Send out to this path actually. And then P4 of 507 is this path. Send. Then P6 see, 709. Okay, send to this path. P2, this is a normal packet. So read the destination IP forward. You can see PE1, P1, P3, P4, P5, P6. Okay. This 1, 2, 3, 4, 5. This 5 router can never decide which path they want to take. Why not P1 take this path? This, and this. Okay, if I want to take this path, why not like this? Why would I like this? Okay, why? 1 hop, 2 hop, 3, 4, 5. But why not 1, 2, 3, 4? Or 1, 2, 3, 4. Why not? Why must this way? So because the first router already decide everything. Everyone, the behind here, everyone must follow. So this is called strict. SRT, SRT with traffic engineering, we purposely control to go this path. Okay, next, if we use a segment ID together, adjacency segment ID with the node ID, means that this is a SRTE but loose, explicit, loose. Means that some forwarding is based on the router own decision, some forwarding is based on the controller decision. Okay, let's say for this PE1, P1 put the label. Okay, 101, 405, 3100. So router read the first label. This is 1101. Okay, according to the configuration, this is the node ID. Node ID means for this 101. So node ID I should swap to 2101. Send to P1. P1 see this 2101. Swap to 3101. P3 see this 3101. So according to the configuration, I should pop the label. Okay, what next? This label. You see, this is an adjacency SID. So pop the label, send out according to this one, because this path is the 405. Send. So P4C, this is 3100 means this router. Okay, what is the best path to go to this router? This one. Okay, so P4 receive this swap the label to 2100. P6, swap the label to 1100, forward to PE2. PE2, port the label forward to the destination. So, means that from PE1 to go to P3, P1 decide, okay? But from here, P3, the control, you must go to this way. Why not go to this way? Faster, right? 1, 2, 3, 4. 4 hop. But now, 1, 2, 3, 4, 5. Okay, but they control this. Okay, they don't control here. They control this, and they don't control here. Means loose. They control some of the path, some of the path not control. So this is loose. This is still SRTE, traffic engineering, but a loose SRTE. So sRGB again, the sRGB. Okay. So sRGB is a segment isolated from the local label resource and is especially used for segment routing. It's also a label, but it's separate from the MPLS label because we don't want to mix the MPLS labels range with the SR labels. We do separate. Both use a different range of labels. Okay. So the node ID is the basic of the node SID, and the globally unique node label must not conflict with the local label. Okay. So this is important here is this why sRGB range of each device is not the same is because different vendor, different implementation. Some are 1000 until 199, some are 2000 until 299, some are 3000 until 3999. Okay. Next one. So working principle. So principle SR here. Same thing. SR is a protocol designed for forwarding data packet on the network based on MPLS protocol and based on the source routing technology. SR divide the destination address prefix, node prefix, and adjacency in the network into segments and allocate SID to these segments. Means that the router itself also has SID. The path itself also has a SID. The destination address also have a SID. This is what I explained, described for you from just now until now. Okay. So working principle as SR, we repeat the same thing again. This is the ISIS, one of the IGP. SRBE control plane. So this PE will share the label, share the label, what to use, and then we start to do the forwarding. Okay, this forwarding. Okay, you see, based on this table. Okay. Node PE1, incoming label 110, out label 210. Okay. Yeah. I see. 210. PE1 push 210 to PE1 to PE1 to PE1 push, and then to 410. Okay, 410 PE1 incoming 210 swap to 410 over to P3. P3 receive incoming 410 swap to 610 forward to PE2. This part, and then PE2 receive 610 out label. Nothing, no label means pop the label, pop. Then the PE will read the destination IP address on the IP header. Then forward. Okay, so this the table on the left is for this path, how to forward. And the table on the right is for this path. Okay, on the bottom. Okay. So this you can read on your own. First, yeah, I mean the same thing. I look at it one by one. Okay, And this is SRBE, and this SRTE will have a controller. Controller will use the BGPRS, PCEP, and netconfig to control everything. All the router use BGPRS to tell the controller what are the network I have, okay, and what is the state cost, and then controller use a PCP, okay, to negotiate, okay, and then controller use a netconfig to send everything to the first router, okay, and then it's the same thing. So everything controller will tell the P1 how to do it, and these are the process I already explained just now. So these are just repeating the same thing. Okay. So which of the following are the SR tunnel type? The SRBE tunnel, SRTE loose, and SRTE strict. Only these three, SRTE loose, SRTE strict, SRBE tunnel. Again, the same thing. Which following actions may be performed when packets are forwarded based on the SR? Push, pop, swap. Please remember these three. Push, pop, swap. Okay. Okay, that's all for the segment routing. Yes.
For that of the adjacency segment.
Adjacency. Okay. Let me just forward, go to that. Okay, agency.
Segment.
This one.
So it's higher. Yeah. Hello?
Hello, yes. Adjacency segment.
So comparing this and the next one, which is the segment, is it? Which is the, this one is the strict, the other one, next?
This is loose.
This one, which has higher cost because of the node that is added. Is there no way, for example, in the first one, the adjacency only,
Yes.
there could sort of be a dynamic adjacency segment configuration? Is it possible? Where at the instance from the beginning, it can determine the most optimal path by constructing the table once before building it. So some sort of an operation that takes place to build up the table once in case the routers move around, so that to recalculate the path before it begins to determine which one will be the strict path. Otherwise, if the routers move around, what do you think will happen in this case?
So if this adjacency segment is just if the router move around, okay, this adjacency segment, they must have a controller, a big brain. Our router must help communicate with the controller. The controller will understand, aware of the whole topology, everything.
Yeah.
You know, this router change to this router. They also need to update the controller. The controller will know everything and do calculations and decide everything, and then tell the first router what are the segment lists to stack, to push on the packet.
Yeah.
Yeah. Okay.
Okay.
Okay, good. Oops. Okay, so is there any other questions? Okay.
Mr. Bell.
Yes.
So if the cost on the working principle of the SRTE, strict explicit part.
Yes. Okay.
So if the cost values of all the links are 1, I'm trying to understand how.
Okay. If for this for strict explicit, the router doesn't care anymore about the cost. They just follow.
Not on the adjacency. The working principle of SRT is strict explicit part data plane.
Yeah, this one SRTE strict.
Down. There's a comprehensive, the one with the controller.
The one with the controller.
Yeah.
This one.
Yeah.
Actually,
No, not the IEs, not the IS, the SRTE.
SRTE.
No, the SRT is strict. Down.
This one.
Oh, right. So if the costs are all 1 and it's strict,
Cost all things are 1.
You know, what specifically is he using to determine the effective path?
Oh, okay. In this diagram, it will tell you why I want to go to this path. Why? Why not this? Okay. The purpose of this is just to tell you the controller can decide how to forward the packet. The controller want to do it this way, or the controller want to do it this way, means that all the router need to follow the instruction. This is what this example try to tell you. Maybe there's a congestion at here. We don't know. Okay, you don't know.
Right.
So all the router will tell the controller update the route. All the router will keep on update the controller what happened. Okay, just like using the telemetry. They are no more using the SNMP. They use a telemetry. Telemetry is real-time update. Okay, they keep on update to the controller what happened to the topology in the whole network. And then maybe there's congestion here, so the controller will tell this P. Okay, now maybe initially they are going to this path, optimal.
Okay.
Sometimes maybe they are congested, so the controller, this router will tell the controller, this path is congested. So controller need to do the calculations and then tell the first router, change the path, change this one.
So it's just determined by the SPF algorithm, then definitely, just how it's constructed.
No, not the SPF algorithm anymore. SPF algorithm is done by the router itself.
No, in the controller. I thought the controller was determining the shortest path between the.
No. Not the router. The controller determine the shortest path. Okay, again, what do you mean by the shortest path? The lowest cost?
Well, it of course has to use some of the attributes like cost to determine, right?
Okay. No. If we based on the cost, this is the best path.
Yeah.
But you see, the controller can do far more because according to the cost is actually based on the bandwidth. Even though either is no congestion or there's a congestion, the path is still same bandwidth. 1 gig is 1 gig. But when there's congestion, the controller can make changes.
Okay.
I don't care whether they don't care about the cost. I see congest. Okay, change path.
Yeah, I can see that.
It's just like a traffic police. See congest here. Okay, direct you to another path.
Okay, that makes sense.
Okay.
All right. Thank you, Mr. Abe.
Okay, thank you.
I have to run off now. I have a meeting. Thank you very much.
Okay, thank you, Dr. Bala. So I finished all the topic today. Okay. Okay. So I have another suggestions. Okay. Let's see. So that's all. We already completed all the topics in HCIA routing and switching. We completed everything. So after this, you can refer to the video recording to do the revisions. Okay. So okay. Apart from this, so I think that's all. That's all for our sessions for these 8 days of the training. Okay. Okay. So regarding the training material, if you still haven't downloaded it, please download from the Huawei Talent. Okay. Then what else? Okay, and here I have I found a website. I found a website on the Google. I found a website on the Google, which is called the lns.infosite.net. Okay. Let me see. Let me put the link on the training info. Training info. I found a third-party website. Okay, lns.infosite.net. Okay, lms.infosite.net. And then, okay, I put this link on the training info. You go and check it out. So this one. Let's see. So this website will give you some preparers help you to do. There's some questions can be used to practice. Can be used to practice for your exam. So you can access to this website and then apply an account. Let me show you how to do it. Okay, I have a login. So login, you can use the. If you haven't used it seen this website before, please create an account. You can create an account. It's free. So and then you can put in your username and password, and then email address is your email address you use to register for this training course. Okay, and then your company or your universities. Okay, and then create a new account, and then you will receive a email verification email in your email. Okay, and then you can log in. After you log in, please go to RNS, and then you choose HCIA RNS. And then these are some tests, some mock tests for you. You can do some of these to get yourself more prepared for the exam. Okay, so all these are free of charge. So you can do this. Try to do some of this before you go to the real exam. Okay. So before this, before you see this page, I think you will see if you click on this HCIRS, I think you will see a enrollment page. So in the enrollment, you just click the enroll. So you just have to make sure the email address you apply, you register for the training. You use or register this account in this website is same as your email you put in the registration form, the trainee registration form for this training. Okay. So the link again, the link I put in the training info, exam preparation. Okay. So I think that's all for today. So, and then I think WhatsApp group will be remain for a few days, I think so. That depends on the first line. So then the lab topology. So I still put all the topology we have gone through. This training along the training topology right here. You can either get it from the WhatsApp group or you can download it from here. Everything. Okay. So I think so. That's all from me regarding the training. Okay. Okay. So if any one of you haven't filled in the feedback form, please register a Hawaii account and then click on the link. Click on the link to fill in the feedback form. Or you can scan. Okay. Scan the QR code to fill in the appraisal form or the appraisal form. Yes. Okay, so